Ladies and gentlemen, today, I'm thrilled to present a systematic review from the esteemed journal Structure and Infrastructure Engineering, published by Taylor and Francis. This review not only delves into the captivating realm of geotechnical slopes but also sheds light on the development of crucial deterioration models. Authored by Roberto J., Marin and Michael Long, this paper highlights a vital aspect of infrastructure management, the often overlooked deterioration of earthwork assets. Why does this research matter, you ask? Geotechnical slopes, like embankments and cut slopes, form the backbone of our infrastructure networks, supporting roads, railways, and various civil engineering projects. However, as time passes, these slopes undergo deterioration due to various factors, including weathering, erosion, and human activities. Understanding their long-term behavior is paramount for effective asset management, ensuring safety, minimizing costs, and maintaining operational efficiency. The systematic review endeavors to answer key questions by exploring existing deterioration models for geotechnical slopes, analyzing methodologies, monitoring techniques, and data collection approaches used over time. It consolidates knowledge from scientific literature, identifying gaps and limitations in current research while emphasizing the importance of proactive maintenance and predictive capabilities in infrastructure management. One notable revelation from the review is the scarcity of comprehensive deterioration models specifically tailored for earthwork slopes. Despite growing interest in the field and an increasing number of research papers addressing the topic, robust models remain elusive. However, the review uncovers a wealth of studies focusing on factors and mechanisms contributing to our understanding of long-term asset behavior. These studies, although not explicitly addressing deterioration models, offer valuable insights for future model development. Moreover, the review emphasizes the significance of monitoring, instrumentation, and data collection in enhancing our understanding of geotechnical asset deterioration. It proposes a framework for long-term analysis, advocating for a combination of laboratory and field tests to improve soil characterization and develop reliable deterioration models. Additionally, it discusses the importance of accurate constitutive soil models that account for long-term deterioration factors influenced by weather and external changes. In conclusion, this systematic review provides invaluable insights for infrastructure professionals and stakeholders. It underscores the need for further research to develop comprehensive deterioration models tailored specifically for earthwork slopes. By advancing our understanding of geotechnical asset behavior, we can better manage infrastructure assets, ensuring their safety, resilience, and longevity. But the exploration doesn't end here. Join us at the upcoming Landslide Scientific Assessment Conference, Slope Dynamics, where we'll delve deeper into these fascinating topics. Scheduled for October 15th to 17th, 2024, this event will be open, free, and online, making it accessible to all interested parties. We'll bring together experts, researchers, and stakeholders to dissect the findings of various groundbreaking research articles related to our event theme. Save the date and stay tuned for more details on how you can be a part of this transformative event. Thank you for your attention. God bless you. Ladies and gentlemen, today, I'm thrilled to present a systematic review from the esteemed journal Structure and Infrastructure Engineering, published by Taylor and Francis. This review not only delves into the captivating realm of geotechnical slopes but also sheds light on the development of crucial deterioration models. Authored by Roberto J., Marin and Michael Long, this paper highlights a vital aspect of infrastructure management, the often overlooked deterioration of earthwork assets. Why does this research matter, you ask? Geotechnical slopes, like embankments and cut slopes, form the backbone of our infrastructure networks, supporting roads, railways, and various civil engineering projects. However, as time passes, these slopes undergo deterioration due to various factors, including weathering, erosion, and human activities. Understanding their long-term behavior is paramount for effective asset management, ensuring safety, minimizing costs, and maintaining operational efficiency. The systematic review endeavors to answer key questions by exploring existing deterioration models for geotechnical slopes, analyzing methodologies, monitoring techniques, and data collection approaches used over time. It consolidates knowledge from scientific literature, identifying gaps and limitations in current research while emphasizing the importance of proactive maintenance and predictive capabilities in infrastructure management. One notable revelation from the review is the scarcity of comprehensive deterioration models specifically tailored for earthwork slopes. Despite growing interest in the field and an increasing number of research papers addressing the topic, robust models remain elusive. However, the review uncovers a wealth of studies focusing on factors and mechanisms contributing to our understanding of long-term asset behavior. These studies, although not explicitly addressing deterioration models, offer valuable insights for future model development. Moreover, the review emphasizes the significance of monitoring, instrumentation, and data collection in enhancing our understanding of geotechnical asset deterioration. It proposes a framework for long-term analysis, advocating for a combination of laboratory and field tests to improve soil characterization and develop reliable deterioration models. Additionally, it discusses the importance of accurate constitutive soil models that account for long-term deterioration factors influenced by weather and external changes. In conclusion, this systematic review provides invaluable insights for infrastructure professionals and stakeholders. It underscores the need for further research to develop comprehensive deterioration models tailored specifically for earthwork slopes. By advancing our understanding of geotechnical asset behavior, we can better manage infrastructure assets, ensuring their safety, resilience, and longevity. But the exploration doesn't end here. Join us at the upcoming Landslide Scientific Assessment Conference, Slope Dynamics, where we'll delve deeper into these fascinating topics. Scheduled for October 15th to 17th, 2024, this event will be open, free, and online, making it accessible to all interested parties. We'll bring together experts, researchers, and stakeholders to dissect the findings of various groundbreaking research articles related to our event theme. Save the date and stay tuned for more details on how you can be a part of this transformative event. Thank you for your attention. God bless you. Ladies and gentlemen, today, I'm thrilled to present a systematic review from the esteemed journal Structure and Infrastructure Engineering, published by Taylor and Francis. This review not only delves into the captivating realm of geotechnical slopes but also sheds light on the development of crucial deterioration models. Authored by Roberto J., Marin and Michael Long, this paper highlights a vital aspect of infrastructure management, the often overlooked deterioration of earthwork assets. Why does this research matter, you ask? Geotechnical slopes, like embankments and cut slopes, form the backbone of our infrastructure networks, supporting roads, railways, and various civil engineering projects. However, as time passes, these slopes undergo deterioration due to various factors, including weathering, erosion, and human activities. Understanding their long-term behavior is paramount for effective asset management, ensuring safety, minimizing costs, and maintaining operational efficiency. The systematic review endeavors to answer key questions by exploring existing deterioration models for geotechnical slopes, analyzing methodologies, monitoring techniques, and data collection approaches used over time. It consolidates knowledge from scientific literature, identifying gaps and limitations in current research while emphasizing the importance of proactive maintenance and predictive capabilities in infrastructure management. One notable revelation from the review is the scarcity of comprehensive deterioration models specifically tailored for earthwork slopes. Despite growing interest in the field and an increasing number of research papers addressing the topic, robust models remain elusive. However, the review uncovers a wealth of studies focusing on factors and mechanisms contributing to our understanding of long-term asset behavior. These studies, although not explicitly addressing deterioration models, offer valuable insights for future model development. Moreover, the review emphasizes the significance of monitoring, instrumentation, and data collection in the world of landslide research. Early warning systems are crucial for saving lives and minimizing damage, especially in regions prone to intense rainfall. One innovative tool making waves in this field is LandScient EWS, a real-time monitoring software designed to track rainfall thresholds and predict landslides. In this new research article, the tool is used in the rugged landscapes of the Colombian Andes, represents a significant advancement in landslide early warning systems. LandScient EWS stands out because it integrates real-time data with predefined rainfall thresholds, allowing it to generate advisory levels that can warn communities of impending landslides. What makes this software particularly noteworthy is its open-source nature, making it accessible to researchers and governments alike who need an effective, customizable tool for landslide risk management. In a case study centered on Medellin, Colombia, LandScient EWS demonstrated its capabilities during a rainfall event that triggered a shallow landslide. The software effectively simulated the advisory levels based on the real-time data, proving its potential as a reliable tool in predicting landslides and providing timely warnings. This case study highlights not only the software's technical prowess but also its practical applicability in real-world scenarios. LandScient EWS isn't just about monitoring, it's about empowering communities and authorities to act before disaster strikes. By offering a user-friendly interface and the ability to adapt to different environments, this software is paving the way for more resilient communities in landslide-prone areas. Its introduction marks a significant step forward in the ongoing effort to protect lives and property from the devastating impacts of landslides. To dive deeper into the fascinating world of landslides and explore the capabilities of LandScient EWS, I invite you to join the Landslide Scientific Assessment Conference. Slope Dynamics. This open, online, and free conference will take place from October 15th to 17th, 2024. Sponsored by LandScient, this event will gather experts and enthusiasts from around the globe to discuss critical issues related to landslide dynamics. Don't miss this opportunity to learn, share, and contribute to the future of landslide risk management. In the world of landslide research, early warning systems are crucial for saving lives and minimizing damage, especially in regions prone to intense rainfall. One innovative tool making waves in this field is LandScient EWS, a real-time monitoring software designed to track rainfall thresholds and predict landslides. In this new research article, the tool is used in the rugged landscapes of the Colombian Andes, represents a significant advancement in landslide early warning systems. LandScient EWS stands out because it integrates real-time data with predefined rainfall thresholds, allowing it to generate advisory levels that can warn communities of impending landslides. What makes this software particularly noteworthy is its open-source nature, making it accessible to researchers and governments alike who need an effective, customizable tool for landslide risk management. In a case study centered on Medellin, Colombia, LandScient EWS demonstrated its capabilities during a rainfall event that triggered a shallow landslide. The software effectively simulated the advisory levels based on the real-time data, proving its potential as a reliable tool in predicting landslides and providing timely warnings. This case study highlights not only the software's technical prowess but also its practical applicability in real-world scenarios. LandScient EWS isn't just about monitoring, it's about empowering communities and authorities to act before disaster strikes. By offering a user-friendly interface and the ability to adapt to different environments, this software is paving the way for more resilient communities in landslide-prone areas. Its introduction marks a significant step forward in the ongoing effort to protect lives and property from the devastating impacts of landslides. To dive deeper into the fascinating world of landslides and explore the capabilities of LandScient EWS, I invite you to join the Landslide Scientific Assessment Conference. Slope Dynamics. This open, online, and free conference will take place from October 15th to 17th, 2024. Sponsored by LandScient, this event will gather experts and enthusiasts from around the globe to discuss critical issues related to landslide dynamics. Don't miss this opportunity to learn, share, and contribute to the future of landslide risk management. In the world of landslide research, early warning systems are crucial for saving lives and minimizing damage, especially in regions prone to intense rainfall. One innovative tool making waves in this field is LandScient EWS, a real-time monitoring software designed to track rainfall thresholds and predict landslides. In this new research article, the tool is used in the rugged landscapes of the Colombian Andes, represents a significant advancement in landslide early warning systems. LandScient EWS stands out because it integrates real-time data with predefined rainfall thresholds, allowing it to generate advisory levels that can warn communities of impending landslides. What makes this software particularly noteworthy is its open-source nature, making it accessible to researchers and governments alike who need an effective, customizable tool for landslide risk management. In a case study centered on Medellin, Colombia, LandScient EWS demonstrated its capabilities during a rainfall event that triggered a shallow land.
Hello again. Welcome to the Landslide Scientific Assessment Conference. It is my honor, my pleasure. I am very happy that today we are in day three, and we had 2 days of excellent presentations. We learned about landslides, slope dynamics, and I am very happy that the list of speakers in this day is exceptional. And I know that some of the people are just going to be connecting, feel invited to share the link to those that are interested, that are studying landslides, and that for sure may be benefited with the topics that we are treating and we are learning about landslides in this event. I want to make some announcements. We are just about to start the next presentation, but in these minutes, I am happy to announce that uh, Sandeep Panchal is going to start with a comparative study of frequency ratio, Shannon's entropy, and analytic hierarchy process, AHP models for landslide susceptibility assessment. Uh, Additionally, I just want to mention that we already uploaded our first video of the uh, conferences presentations that we had during days 1 and 2. I am talking about the presentation of Dr. Susana Pereira. The video is already available in the LandScient YouTube channel, so you can download it, or let's say you can watch it there in our channel. And we had some issues, technical issues in the live streaming, but now this video is in good quality and complete in the channel. So we invite you to watch the video there. In some minutes, we are going to start with our first presentation. We are right now. I am honored to welcome Dr. Sandeep Panchal. Thank you so much for accepting the invitation to present at the Landslide Scientific Assessment Conference. How are you, Doctor?
Uh, Thank you, Dr. Marin, for inviting me for this season also. I am good. How are you?
Excellent. I am very well, thank you. Thank God. So
Okay.
all the time is yours. So go ahead and uh, feel free to share all what you prepared for us. Thank you.
Okay. Greetings of the day, ladies and gentlemen. My name is Dr. Sandeep Panchal, and I am currently working at Department of Civil Engineering, Government Polytechnic, Mankeda, Agra. But this work, a comparative study of frequency ratio, Shannon's entropy, and analytic hierarchy process models for landslide susceptibility assessment, is conducted during my PhD and at Delhi Technological University. And this work is conducted under guidance of Professor Amit Kumar Srivastava. So these are the contents. So let's begin with the backgrounds and the introduction. The hilly regions are frequently affected by landslide disasters. Landslides are responsible for huge loss of life and damage to the infrastructure. The uh, the countries, the hilly region in the developing countries like India, uh, is rapidly growing, and there are huge anthropogenic activities and other kind of activities that are triggering the movement of landslides. So a landslide is a result of movement of slope under the impact of gravity, but this movement can be triggered by different factors such as rainfall, earthquakes, erosions, etc. So the accurate prediction of landslides can help in planning and management of landslide hazard, and can ultimately use to reduce the risk of the landslide hazard. So landslide susceptibility map and microzonation of landslide susceptibility is a tool that can help in identifying the landslide prone area. These maps can help in in planning and management of landslide hazards, and these are very efficient tool for planners and risk managers. Uh, so according to, let's begin with the definition of landslide susceptibility. According to Geological Survey of Ireland, a landslide susceptibility map identifies the area which are subject to landslides, and it's measured from low to high. In nutshell, in landslide susceptibility mapping, we take a map, or we take a study area, and then we divide the study area into 3-4 zones that shows the susceptibility of occurrence of landslides in different zones of the study area. So microzonation of landslide susceptibility take into account where the landslide occur and what caused them. So the susceptibility maps consider the spatial part of the occurrence of landslides, uh, and calculates the landslide potential in the different zones of a study area. So these are the objectives of the study, our objectives of this study. The first objective is to understand the role of different causative factors of landslide, that what kind of factors are responsible for occurrence of landslide, and what may be the contribution of these factors towards occurrence of landslides. Second, to prepare the landslide inventories for Shimla district in Himachal Pradesh. Himachal Pradesh is a province in India, and Shimla is the capital of Himachal Pradesh. Uh, this study is based for that study area. So our second aim is to prepare the landslide inventories. Some of the landslide inventories are available. The rest are prepared with some field surveys and some literature reports that are available on the historical landslides. The third objective is to perform the landslide susceptibility mapping with different methods. We have considered 3 methods. We will discuss how or why did we consider this method and all. And the fourth objective is to compare these different methods and suggest more suitable method for this study area, and what are the advantages and disadvantages of these techniques for landslide susceptibility mapping. And the case study is for particularly for the Shimla region. So these are the details of the Shimla region, where our study area is based on. The study area lies between longitudes 77 degrees 0 minute east, 78 degree 19 minute east, and latitudes are from 30 degree 45 minute and 31 degree 45 minute north. This can be shown in the figure. In the next slide, I will show the figure that how the area is extracted. It is surrounded by other districts that are hub uh, for the tourism activities. The elevation of the study area, the elevation is variable, and it varies from 300 meter to 6,000 meter from mean sea level. The climate is moderately warm to cool in the winters, and currently the average temperature lies between 4 degrees Celsius to 31 degrees Celsius. It is the average temperature. However, the temperature go in like -3, -4 degrees Celsius whenever it comes to the minimum temperature of the study area. So this is the study area. This is Indian continent map. And here lies the Himachal Pradesh, which is a province. And here is the Shimla, the district of Himachal Pradesh. And the red colored dots shows the landslides, which are not these are not the scaled landslide. We have enlarged the landslides to show them in this figure. However, these are very small dots, and the elevation varies from low to high. And this is our study area. So for this study area, we will try few methods to prepare the landslide susceptibility map. We would like to divide this area into different zones according to its susceptibility towards occurrence of landslides. So let's come to the literature review. We considered more than 150 papers for this literature review. However, we have summarized the literature review in nutshell. So we have divided the techniques of landslide susceptibility mapping into 3 categories. These three type of techniques are qualitative techniques, quantitative techniques, and semi-qualitative or semi-quantitative techniques. The qualitative techniques are the techniques which are based on the opinion of expert. The causative factors of occurrence of landslides are considered and are selected by the expert, and the expert tells that what causative factor is contributing up to what extent towards the occurrence of landslides. The evaluator select the causative factor and their relative importance. This is the techniques that lies in qualitative techniques category are very simple to implement. And what we find from the literature review that accuracy is a challenge in expert-based techniques. The techniques which are purely based on expert uh, maybe get impacted by the biasness of the experts. The hazard maps can vary from expert to expert as it is purely based on the opinion of expert. So the accuracy is a challenge for these techniques. However, where there is no landslide inventory available, and if you want to go for landslide susceptibility mapping in such areas where historical data for the landslide are not available, at that situation, one can go for qualitative techniques. They can be used in the absence of landslide inventories. Second are quantitative techniques. The quantitative technique establishes mathematical relationship between occurrence of landslide and the causative factors. So different causative factors are considered and statistical or mathematical relationship are established between these factors and the subfactors and occurrence of landslide.
Mm, yes. I'm sorry. Uh, some internet connections, some issues, internet connection issues. We are waiting if Dr. Sandeep Panchal can connect again.
Ladies and gentlemen, today, I'm thrilled to present a systematic review from the esteemed journal Structure and Infrastructure Engineering, published by Taylor and Francis. This review not only delves into the captivating realm of geotechnical slopes but also sheds light on the development of crucial deterioration models. Authored by Roberto J., Marin and Michael Long, this paper highlights a vital aspect of infrastructure management, the often overlooked deterioration of earthwork assets. Why does this research matter, you ask? Geotechnical slopes, like embankments and cut slopes, form the backbone of our infrastructure networks, supporting roads, railways, and various civil engineering projects. However, as time passes, these slopes undergo deterioration due to various factors, including weathering, erosion, and human activities. Understanding their long-term behavior is paramount for effective asset management, ensuring safety, minimizing costs, and maintaining operational efficiency. The systematic review endeavors to answer key questions by exploring existing deterioration models for geotechnical slopes, analyzing methodologies, monitoring techniques, and data collection approaches used over time. It consolidates knowledge from scientific literature, identifying gaps and limitations in current research while emphasizing the importance of proactive maintenance and predictive capabilities in infrastructure management. One notable revelation from the review is the scarcity of comprehensive deterioration models specifically tailored for earthwork slopes. Despite growing interest in the field and an increasing number of research papers addressing the topic, robust models remain elusive. However, the review uncovers a wealth of studies focusing on factors and mechanisms contributing to our understanding of long-term asset behavior. These studies, although not explicitly addressing deterioration models, offer valuable insights for future model development. Moreover, the review emphasizes the significance of monitoring, instrumentation, and data collection in enhancing our understanding of geotechnical asset deterioration. It proposes a framework for long-term analysis, advocating for a combination of laboratory and field tests to improve soil characterization and develop reliable deterioration models. Additionally, it discusses the importance of accurate constitutive soil models that account for long-term deterioration factors influenced by weather and external changes. In conclusion, this systematic review provides invaluable insights for infrastructure professionals and stakeholders. It underscores the need for further research to develop comprehensive deterioration models tailored specifically for earthwork slopes. By advancing our understanding of geotechnical asset behavior, we can better manage infrastructure assets, ensuring their safety, resilience, and longevity. But the exploration doesn't end here. Join us at the upcoming Landslide Scientific Assessment Conference, Slope Dynamics, where we'll delve deeper into these fascinating topics. Scheduled for October 15th to 17th, 2024, this event will be open, free, and online, making it accessible to all interested parties. We'll bring together experts, researchers, and stakeholders to dissect the findings of various groundbreaking research articles related to our event theme. Save the date and stay tuned for more details on how you can be a part of this transformative event. Thank you for your attention. God bless you.
Okay, we are back, and I am honored to introduce and present Dr. Massimiliano Bordoni. Thank you so much for accepting our invitation, our direct invitation to be part of the Landslide Scientific Assessment Conference. How are you, Doctor?
I'm fine. Thank you, Roberto, for the introduction and for having inviting me to to this very interesting conference. So I'm very happy to present this topic of my research activity to you and to all the people connected.
Okay, so this is your time, and so you can start whenever you want. Thank you.
You're welcome. Okay, thank you all. First of all, I want to introduce just myself. I am Massimiliano Bordoni. I am a research assistant in engineering geology at the University of Pavia in Italy. And today I want to introduce a topic of my research activity that is related in particular to land use, to the land use effects on the triggering and on the predisposing occurrence of a particular type of landslide that are shallow landslides. I want also to thank my colleague, my supervisor, Professor Meisina, and Dr. Vivaldi that are helping me during this year in this work that was also finalized in a publication in Science of the Total Environment. You can find some references on the presentation during the slides. So, the title of my presentation is Impact of Mechanical and Hydrological Reinforcement Effects of Cultivated Plants of Shallow Landslides. As you can see from the title, the aim of this presentation is related to see which could be the effects of different cultivated plants on the reinforcement guaranteed to soil to avoid the occurrence of shallow landslides. First of all, a brief introduction on rainfall-induced shallow landslides that are the phenomena we are studying. And in particular, these are a movement of soil or mass of debris that is generally induced by rainwater infiltration that and also interested the first layers of soil. And in particular, typically have a different depth of the sliding surfaces, but between a few tens of centimeters to less than 2 or 3 meters in depth. These phenomena typically have different volumes of displaced materials, even if they aren't so big. But a problem is related to the fact that during a triggering event, many phenomena can affect little catchments or also single slopes. So there is a very high density that even if the phenomena are not so big, can provoke severe damages to people, infrastructures, economy, and environment. These phenomena are very fast. In fact, according to this classification, you can see that can be classified from rapid to extremely rapid. So they can be triggered and they can conclude in just minutes or seconds sometimes. So the approaches to study the phenomena have to be chosen according to this particular kinematic behavior. And in particular, this phenomena has to be taken into account during the characterization of the involved materials, the monitoring, the prediction, the analysis of hazard and risk assessment, and also the possible mitigation in the most prone areas. In this presentation, I want to focus in particular on possible tool for mitigating this phenomena according to a sustainable solution. In fact, one of the main predisposing factors of this phenomena is related to the land use, or also the land use changes during time. In fact, in general, the proneness of shallow landslides in a territory is strictly dependent on the type of the land use that is present in the hill slopes. And also there can be observed an increase in landslide susceptibility in correspondence of areas where there was a recent land use change. For example, there are some examples all over the world about these consequences in Italy, but also in other countries susceptible to landslides. This path is also accelerated, for example, in northern area or closer to polar sectors in correspondence of permafrost thaw in high altitude and high latitude territories that can provoke an increase in water content and pore water pressure, leading to a reduced shear strength. This is not related to this presentation, but is important to be understood as another possible land use effect. So the aim of this presentation is to analyze in particular possible, which is the effect of different land uses and different land covers on the development, on the predisposing conditions to shallow landslides, and in particular to find if there is the possibility of particular agricultural management that can reduce the possibility of occurrence of landslides. This is a sort of mitigation, development of specific and innovative methodologies, according also to different scales of analysis and data variability, to reduce the probability of occurrence of these landslides over large territories. In particular, we want to see some solutions that could be also sustainable solutions in response to the Sustainable Development Goals produced by ONU Agenda 2030. But which is the effect of the plants on shallow slope stability? In these pictures, you can see a sort of summary of all the effects produced on plants on a hill slope. And in particular, we have to focus on the effects produced by the roots present in the soil. Roots typically have two effects. A mechanical reinforcement guaranteed by the presence of the roots that can increase the shear strength of the soil, and a hydrological reinforcement that is also called root water uptake. That is the reduction of pore water pressure induced by an uptake of water from roots to plants for plant health and activity. In general, we can conclude that more roots are present in the soil, more is the root reinforcement, and lower is the probability of occurrence of shallow landslide. So we can try to see if different agricultural management and land cover can influence soil properties and root reinforcement to have a direct effect on the landslide probability of occurrence in order to have a sort of action of mitigation and prediction over large territories. The mechanical reinforcement of soil provided by different cultivated plants, to monitor and compare also the soil hydrological responses and the hydrological reinforcement effects of these different cultivated plants, and to evaluate and compare the influence of both mechanical and hydrological effects in terms to see which are the effects of each of these ones on the susceptibility to rainfall-induced shallow landslides, and to determine whether the mechanical and hydrological reinforcements can enhance or hinder slope stability. We have studied particular land uses, focusing on the most widespread land uses present in Oltre-Popavese area. Oltre-Popavese area is a sector, a hilly sector of the northern Italian Apennines that is very representative of an area that is very prone to shallow landslides and soil erosion that are causing recently severe damages to agriculture, and in particular to the slope vineyards, which is the most important economic branch of this territory. We wanted to see which were the effect of hydrological and mechanical reinforcement on different agricultural management in vineyards and comparing also with other cultivated plants widespread in the study area. We focusing in particular on vineyards with permanent grass cover in the interrows, vineyards with an alternating of tillage and grass cover in the interrows, and sowed fields with simple grasses such as Medicago sativa. From a geological and geomorphological point of view, we have chosen 3 test sites, in particular in the central Oltrepo Pavese area, where bedrock is quite similar, particular alternance of marls, sandstones, flishes, and melanges, and also the soil cover is very similar in order to control all the factors that could influence the predisposing occurrence of landslides and to see which was the effect just of the reinforcement. The test sites were characterized by different presence of landslides or not, but generally all of these test sites are medium steep slopes and are characterized by presence of clay soils with a high content of clay and silt and a high plastic behavior in terms of Casa Grande classification. From the methodology approach, in substance, the objective was to analyze which was the effects in terms of reinforcement. And in particular, we have carried out 2 different approaches. The first approach is to see which was the effect of root mechanical properties and root density in terms of root mechanical reinforcement. This was carried out, in particular, measuring the root density and the root mechanical properties of the different cultivated plants to reconstruct a profile of root mechanical reinforcement according to the root bundle model technique. Instead, for the analysis of the hydrological root reinforcement, we have installed different hydrological monitoring stations to monitor the trend in times of the soil hydrological parameters at the different depths. In particular, water content and pore water pressure in correspondence of the layers present in the soil profile. The resolution of these hydrological monitorings is very high in terms of minutes or hour and is allowed by a set of water content and pore water pressure probes. Let's pass to the results. From the analysis of the root mechanical reinforcement, it's evident that different cultivated plants can allow different types of root mechanical reinforcement. And in particular, the highest is the root density, the highest is the mechanical reinforcement provided by the plants on the soil. In this case, the highest mechanical reinforcement was provided by the alternating vineyards. In terms of root hydrological reinforcement, the situation is quite similar. The plants where we have higher root density, they are also able to have a higher root water uptake. This was translated in a reduction in saturation degree along time, but also a reduction in pore water pressure along time, because less water is probably present in the soil all along the soil profile. So, this reduction in these hydrological parameters is transformed in an increase of the hydrological root reinforcement, because less is the pore water pressure that is present in the soil. And this is evident not just in the summer, where according to the evapotranspiration and the use of the water by plants, the use of the water is higher, but also during wet season, such as in spring and in autumn and sometimes also in winter. And this has a direct impact in terms of slope stability, because both reinforcement types on shallow slope stability determines a different probability of occurrence according to shallow landslides. In general, the land uses with the highest root densities have also the highest root reinforcement, both in terms of mechanical and hydrological reinforcement. But according to this, the slope safety factor can be higher, and then the probability of occurrence of shallow densities can be reduced. In particular, if we focus in vineyards, especially in correspondence of the alternating vineyards, where we quantified the highest values of mechanical and hydrological reinforcement, the hydrological reinforcement effect could be observed also during wet seasons, such as autumn, winter, and spring, giving also contribution to slope stability where shallow landslides are more probable. This situation occurs when plants uptake enough water from soil to reduce significantly the pore water pressure, guaranteeing in particular an increase in terms of hydrological reinforcement of 3 kilopascal, from 1 to 3 kilopascal, at the typical depth of the sliding surface that are very similar to the measure of mechanical reinforcement. So, we can conclude that these results suggest that both hydrological and mechanical effects of vegetation can have a particular impact in susceptibility towards shallow landslides, helping in the selection of the best land uses that can reduce the probability of occurrence of these failures over larger territories. In general, vineyards, characterized by higher density, are also characterized by a higher root mechanical reinforcement. But the land uses in vineyards with the highest density have also a highest root water uptake, and as a consequence, the highest root hydrological reinforcement. The root hydrological reinforcement is evident all over the year, not just in summer, but also in wet period, where shallow landslides are more probable. This situation occurs when plants uptake enough water from soil to reduce significantly the soil pore water pressure, guarantees an increase in hydrological reinforcement from 1 to 3 kilopascal at the typical depth of the sliding surface of shallow landslides in this area, with values that are similar of the ones of mechanical road reinforcement. Obviously, this research is just the first step. Future developments should be also the analysis of the role played by other agricultural managements or other cultivated plants in this study area or in similar context. I want to thank this project that was funded by Italian and European institutions that allows this research, and I also want to thank you for the attention.
Thank you. Thank you so much, Dr. Maximiliano. I am going to invite. I am just taking a look at the chat. So thank you for sharing. We have still some minutes. I would like to ask a question by myself. I have studied the effect of plants on slope stability. Did you find any or challenges when defining or selecting right parameters and defining their values in your analysis, specifically about the effect of the plants in the slope stability?
Typically, the measure of the mechanical reinforcement provided by roots is carried out by field measures of the root density that is then coupled by other techniques. For measuring the mechanical reinforcement, we have measured the root density and also the root mechanical properties in laboratory, in particular the tensile and elastic strength properties of the roots. Then these measures are combined together in a model that is called the root bundle model. And this allows us to measure the root mechanical reinforcement at different depths. From the hydrological reinforcement, it's a sort of measure of the pore water pressure that is gained when roots uptake water from the soil. So we need an hydrological monitoring in correspondence of different land uses to quantify the differences in terms of pore water pressure, obviously according to the same climatic conditions, induced by the roots that are able to take water from the soil.
Great, wonderful. Congratulations on your excellent work. Yeah, I'm pretty sure that we have a lot to learn, and this is a challenge for all those who are, or we have been modeling slope stability and landslide occurrence, but commonly neglecting the effect of something that so important, and to study the impact of the mechanical and hydrological reinforcement of cultivated plants specifically is an excellent approach. So thank you so much for sharing
Thank
today
you
your
again
presentation.
for this invitation.
Okay, goodbye. All right, we are back here at the Landslide Scientific Assessment Conference. It is my honor to introduce Dr. Sanjita. Maybe in some uh, seconds, she's going to start with the presentation. Before that, I am going to remind all those who uh, registered and that I have received emails about the certificate of participation of the event to attendees, participants. We have been, or we are uh, sending you via email on the request for all the speakers. The certificate is going to be sent also via email. You don't have to request it because we are going to send it to you anyway. So this is some of the questions I have received. So we are just about to start with a presentation of Dr. Sanjita. Uh, okay, now stay there. Hello, Dr. Sanjita. How are you? And welcome.
Hi, thank you, Roberto. I'm good.
That's great. I am very glad that you are connected from Ireland. I love Ireland. So it was my pleasure to know that you are doing research there. And I hope that what you prepare today may be very valuable to all of us, that we are lovers of the topics related to Landslide. So before you start, I would ask you that very briefly introduce yourself and you can start with your presentation. Thank you so much.
Thank you. So, very good afternoon, good morning to everyone. I'm Dr. Sangeeta. First of all, I would like to thank you, Roberto, for this opportunity and conducting this very innovative platform for the landslide research. So, I'm Sangeeta. I'm doing my postdoctoral research at University College Dublin. And previous to that, I have completed my PhD from IIT Roorkee, India, and I have worked on the landslide susceptibility zonation mapping. So today I will present a topic, influence of anthropogenic activities on landslide susceptibility, a case study in Solan district, Himachal Pradesh. So in this presentation, I will start with the global and Indian scenario of landslide. Then I will discuss some research gap in this topic and the main objective of this research work, followed by the data used, material and methods, and I will discuss the result and the future direction and the conclusion. So we all know landslides are very severe, geohazard, and frequently occur in countries including China, Italy, Indonesia, Japan, Philippines, United States, Switzerland, and many more. And these hazard is not only limited to this country; they are also occur the countries which are straddled by the Himalaya, like Nepal, Pakistan, India. If we talk about numbers, in past 2 decades, approximately 4.8 million people have been affected and more than 18,000 people have lost their life. Now coming to the Indian scenario, here in this world map, you can see the position of India, which is the most affected in terms of fatal events related to landslide. And if we talk about the situation of India inside the India, about 15% of the land area is prone to landslide. And most of the area is falling into northwest and northeast Himalaya. Here in this Indian map, you can see these yellow points are the distribution of the landslide. Here you can see 34% falls in a northwest Himalaya and 43% falls in a northeast Himalayas. Before coming to the presentation, I will discuss what is landslide susceptibility zonation, how we develop these maps. So landslide susceptibility zonation is basically subdivision of the terrain into zones that have a different likelihood for the landslide occurrence. In order to develop landslide susceptibility zonation map, we follow the philosophy given by Brab in 1991. The past and the present are the key to the future. So here, the past is the landslide inventory, which is the past record of the available landslide events. And the present is the landslide controlling parameter, which are the inherent controlling parameters for the landslide. So with the help of this two input parameter, that is landslide inventory and landslide controlling parameter, we use some landslide methods and we develop landslide susceptibility zonation map. And with some validation methods, we check the accuracy and the acceptability of the maps. So landslide could be triggered by different triggering factors. Some are natural, some are anthropogenic. In a natural, the common triggering factors are rainfall, seismic activity, and for the anthropogenic parameters, some factors like road development, tunneling, hydroelectric power projects, and climate change. So many recent literature suggests that anthropogenic activities alter the topography. Altering the topography means changing the terrain of the area, which eventually lead to the unstable terrain and become a landslide disaster. Many studies have reported that road construction or widening of the road and land use land cover changes have a significant influence on the landslide occurrence. So there is many studies which have covered the topics related to the rainfall induced landslide or earthquake induced landslide, but in the literature there is still a gap which on the detailed information about the anthropogenic activities and climate change, how these factors affect the landslide occurrence. So this is the main research gap in this domain. Based on this research gap, the main objective of this work is to understand the influence of anthropogenic activities on the landslide susceptibility. So for this work, various inherent landslide positive parameters, which include the topography, geology, lithology, and different other parameters, with the dynamic anthropogenic factors used to develop the landslide susceptibility zonation map by the help of the statistical based frequency ratio method. So for this work, I have selected an area which falls in Himachal Pradesh, India. This is the Solan district. And why I have selected this area have the very socio-economic importance in the region. And this area is also known as the gateway to the Himachal Pradesh because one of the major highway NH5 passes through this district. So this is the location map of the study area. Now coming to the data, material and methods. As I have discussed earlier, to develop a landslide susceptibility zonation, we require two basic input parameter. One is landslide inventory and other is landslide controlling parameters. So first step is to collect in the data, processing the data. So here is the different sources from where I have collected the raw data and processed them with the help of ArcGIS and different tools. So the first step to collect the data, process the data, and then I have used some statistical method, that is frequency ratio, and develop the landslide susceptibility zonation map and validate this map with the different techniques. And at the end, I have analyzed the impact of anthropogenic activities on the landslide susceptibility zonation and how land use land cover affected the landslide occurrence. So there are several methods available by which we can develop the landslide susceptibility zonation map. There is two main categories, qualitative and quantitative. So in a qualitative method, in the absence of landslide inventory, basically we use the distribution free or geomorphic analysis. This is basically based on the expert judgment. And the other category is quantitative, where we use the correlation between the landslide controlling parameters and the landslide occurrence. So in this particular work, I have selected a statistical based bivariate method. So in this, we correlate a landslide distribution with the landslide controlling parameter. Then we normalize this value by using relative frequency ratio, and then use the weighted linear combination to generate the landslide susceptibility index. So this is the first input, that is landslide inventory. How we define the landslide inventory? Basically, this is the detailed register of the distribution and characteristics of the past landslide. So I have categorized my landslide inventory in a two category based on the triggering parameter. One set is rainfall induced landslide and the other set is human induced landslide. So how we categorize the human induced landslide? This is the landslide that are directly or partially triggered by the anthropogenic activities. This anthropogenic activities could be the modification of the topography, change in the water circulation, or change in the land use, land cover. So based on the different driving factors that are slope profiling, urbanization, or using the different vibration or explosive technique, they alter the terrain, they alter the stability of the slope. So based on this parameter, like road in a road widening, sometime road cutting at a very steeper angle, or the disturb the original natural stabilized slope. So based on this driving factor, we categorize our slope as a human induced landslide. So a total 1030 landslides have been used in this study in a form of polygon data. Now coming to the landslide positive parameters. So here the first set is the landslide positive parameter, which are the inherent parameters. So in this, I have selected three topographical factors: slope angle, aspect, and curvature. Then the lithology and lineament and drainage. So each controlling parameter affect the landslide in a different way. So first we have to understand how these parameters are going to affect the landslide, how these parameters are related with the landslide. So for this, we use the frequency ratio to find a correlation between the parameter and landslide. So for example, slope angle is, if we increase the angle of slope, the chances of landslide would be higher. Similarly, for the aspect, in a Himalayan region, south-facing slopes are more prone to landslide because they receive the higher rainfall. Similarly, the other parameter like structural discontinuity in terms of lineament has been used. And for the anthropogenic factors, the dynamic, which are dynamic in nature, change year by year or month by month, we have selected land use, land cover for the 5 years, ranging from 2017 to 2021. So here are the two land use, land cover map. One is from the 2017 and other from the 2021. So here you can see area covered by tree decreased by more than 12%. Here in the bar chart, you can see. And the other, like crops, built up scrub or the bare land has increased. So landslide incidences have increased significantly in both built area and the bare land. From year 2017 to 2021, there is increase in the landslide occurrence. Now coming to the landslide susceptibility generation mapping. So as I have mentioned earlier, we have select the input parameter like landslide inventory and landslide controlling parameter. Then we use some methods like frequency ratio method or any other method to find the correlation. And then we use the weighted linear combination to generate the landslide susceptibility index range. And we use some classification method to divide our landslide susceptibility zone in a different groups, which ranging from very low susceptibility to very high susceptibility. So the very fundamental rule to check if we have developed the accurate map or not, our very high susceptibility class should have the lowest area and the highest number of landslide occurrences. Then to check the accuracy of the map, we use validation technique. Here I have used the success and prediction rate curve. As I have mentioned earlier, I have categorized my landslide in a training and testing data set. I have keep 80% to train the model and 20% to validate the model. So here the success rate curve which use the training data set and the prediction rate curve use the testing data set. So here you can see the accuracy, the area under curve is 0.79 for the training data set, that is success rate curve, and 80% for the prediction rate curve. Now coming to the evaluation of LULC and LSZ. So here are the two landslide susceptibility zonation map. One for the year 2021, which used the land use land cover map for the same year, and the other which used the land use land cover from the 2017 year. So here you can see the map which used the land use land cover map for 2021. In that, 23% area falls into high susceptibility and very high susceptibility classes, and 48% area falls into very low susceptibility and low susceptibility classes. If we compare this map with the landslide susceptibility zonation map from the 2017, we can see the high susceptibility and very high susceptibility classes have been increased by 15%, and the low susceptibility classes and very low susceptibility classes reduced by the 7%. So this basically signified the impact of the change in a land use land cover over the time and how this impact the landslide susceptibility zonation. Now coming to the landslide analysis on the national highways. So for this purpose, we have selected 4 different national highways, and we have created a 1 kilometer buffer along the national highway, then conduct the landslide analysis. So basically road construction, which include the new roads or the widening project, are one of the main anthropogenic activities in the Himalayan region. So here you can see the first one is the National Highway 5, which is the main highway which passes through this study area. So a total 232 landslide are falling in the buffer zone, which is 1 kilometer. And out of this, 83 landslides are due to anthropogenic activities. So here's some pictures from this area. This is the event in 2021. So the main conclusion from this study, there's 3 main findings. The one is landslide susceptibility is higher along the road network, and most of the landslides which are along the road are not the rainfall induced, those are the human induced landslides. And more than 50% are triggered due to the anthropogenic activities. So one of the main reason in the area is anthropogenic activities. So area belonging to high susceptibility classes have been increased, whereas lower susceptibility classes have been reduced. So in future, the inclusion of landslide susceptibility, inclusion of the land use, land cover, the changes in the terrain should be included in the analysis of the landslide susceptibility zonation. So these are some key references I have used in my presentation. This is the paper I have presented today. You can find this for more details. So with the note, we cannot stop disaster, but we can be prepared to survive them. With this note, I will end my presentation. If you have any questions, you can drop in a chat box, or you can contact me on this email IDs. Thank you. Roberto, I'm not able to hear you.
Yeah. Oh, yes,
Yeah,
sure.
yeah, now. Yeah,
Thank you for sharing me now. Yes, I was saying that thank you for your presentation. Thank you for uh, your, to prepare it, and congratulations on your research and advancement. Uh, I
thank
was
you.
I was saying that those who maybe watch the video after days or later, feel free to write to the email that Dr. Sanjita shared. So I think we have right now a break. We are going to continue in around 10 minutes with our next presentation. So I thank you again, Sanjita, and so I hope to see you soon.
Thank you. Thank you.
Ladies and gentlemen, today, I'm thrilled to present a systematic review from the esteemed journal Structure and Infrastructure Engineering, published by Taylor and Francis. This review not only delves into the captivating realm of geotechnical slopes but also sheds light on the development of crucial deterioration models. Authored by Roberto J., Marin and Michael Long, this paper highlights a vital aspect of infrastructure management, the often overlooked deterioration of earthwork assets. Why does this research matter, you ask? Geotechnical slopes, like embankments and cut slopes, form the backbone of our infrastructure networks, supporting roads, railways, and various civil engineering projects. However, as time passes, these slopes undergo deterioration due to various factors, including weathering, erosion, and human activities. Understanding their long-term behavior is paramount for effective asset management, ensuring safety, minimizing costs, and maintaining operational efficiency. The systematic review endeavors to answer key questions by exploring existing deterioration models for geotechnical slopes, analyzing methodologies, monitoring techniques, and data collection approaches used over time. It consolidates knowledge from scientific literature, identifying gaps and limitations in current research while emphasizing the importance of proactive maintenance and predictive capabilities in infrastructure management. One notable revelation from the review is the scarcity of comprehensive deterioration models specifically tailored for earthwork slopes. Despite growing interest in the field and an increasing number of research papers addressing the topic, robust models remain elusive. However, the review uncovers a wealth of studies focusing on factors and mechanisms contributing to our understanding of long-term asset behavior. These studies, although not explicitly addressing deterioration models, offer valuable insights for future model development. Moreover, the review emphasizes the significance of monitoring, instrumentation, and data collection in enhancing our understanding of geotechnical asset deterioration. It proposes a framework for long-term analysis, advocating for a combination of laboratory and field tests to improve soil characterization and develop reliable deterioration models. Additionally, it discusses the importance of accurate constitutive soil models that account for long-term deterioration factors influenced by weather and external changes. In conclusion, this systematic review provides invaluable insights for infrastructure professionals and stakeholders. It underscores the need for further research to develop comprehensive deterioration models tailored specifically for earthwork slopes. By advancing our understanding of geotechnical asset behavior, we can better manage infrastructure assets, ensuring their safety, resilience, and longevity. But the exploration doesn't end here. Join us at the upcoming Landslide Scientific Assessment Conference, Slope Dynamics, where we'll delve deeper into these fascinating topics. Scheduled for October 15th to 17th, 2024, this event will be open, free, and online, making it accessible to all interested parties. We'll bring together experts, researchers, and stakeholders to dissect the findings of various groundbreaking research articles related to our event theme. Save the date and stay tuned for more details on how you can be a part of this transformative event. Thank you for your attention. God bless you. Ladies and gentlemen, today, I'm thrilled to present a systematic review from the esteemed journal Structure and Infrastructure Engineering, published by Taylor and Francis. This review not only delves into the captivating realm of geotechnical slopes but also sheds light on the development of crucial deterioration models. Authored by Roberto J., Marin and Michael Long, this paper highlights a vital aspect of infrastructure management, the often overlooked deterioration of earthwork assets. Why does this research matter, you ask? Geotechnical slopes, like embankments and cut slopes, form the backbone of our infrastructure networks, supporting roads, railways, and various civil engineering projects. However, as time passes, these slopes undergo deterioration due to various factors, including weathering, erosion, and human activities. Understanding their long-term behavior is paramount for effective asset management, ensuring safety, minimizing costs, and maintaining operational efficiency. The systematic review endeavors to answer key questions by exploring existing deterioration models for geotechnical slopes, analyzing methodologies, monitoring techniques, and data collection approaches used over time. It consolidates knowledge from scientific literature, identifying gaps and limitations in current research while emphasizing the importance of proactive maintenance and predictive capabilities in infrastructure management. One notable revelation from the review is the scarcity of comprehensive deterioration models specifically tailored for earthwork slopes. Despite growing interest in the field and an increasing number of research papers addressing the topic, robust models remain elusive. However, the review uncovers a wealth of studies focusing on factors and mechanisms contributing to our understanding of long-term asset behavior. These studies, although not explicitly addressing deterioration models, offer valuable insights for future model development. Moreover, the review emphasizes the significance of monitoring, instrumentation, and data collection in enhancing our understanding of geotechnical asset deterioration. It proposes a framework for long-term analysis, advocating for a combination of laboratory and field tests to improve soil characterization and develop reliable deterioration models. Additionally, it discusses the importance of accurate constitutive soil models that account for long-term deterioration factors influenced by weather and external changes. In conclusion, this systematic review provides invaluable insights for infrastructure professionals and stakeholders. It underscores the need for further research to develop comprehensive deterioration models tailored specifically for earthwork slopes. By advancing our understanding of geotechnical asset behavior, we can better manage infrastructure assets, ensuring their safety, resilience, and longevity. But the exploration doesn't end here. Join us at the upcoming Landslide Scientific Assessment Conference, Slope Dynamics, where we'll delve deeper into these fascinating topics. Scheduled for October 15th to 17th, 2024, this event will be open, free, and online, making it accessible to all interested parties. We'll bring together experts, researchers, and stakeholders to dissect the findings of various groundbreaking research articles related to our event theme. Save the date and stay tuned for more details on how you can be a part of this transformative event. Thank you for your attention. God bless you. Ladies and gentlemen, today, I'm thrilled to present a systematic review from the esteemed journal Structure and Infrastructure Engineering, published by Taylor and Francis.
So we are back. It is my honor. I am here with Dr. Stefano Luigi Gariano. Just in 1 minute, he's going to start his presentation, and I am going to uh, encourage all those who are connected that you can share the link, you can share the uh, video with those who may be interested in the topics that we are learning, that we are treating today at the Landslide Scientific Assessment Conference. Just uh, a very interesting topic, predicting rainfall in the landslides in a changing climate, data, tools, and challenges from a regional scale perspective. This is what we are going to uh, hear and watch in the presentation of Dr. Stefano Luigi Gariana. Hello, doctor. How are you?
Thank you, Roberto. Thank you for this kind presentation. Just tell me when I have to start.
So we are ready. So it is your time. Yes, I am going to ask you. As I have requested other speakers, maybe you can introduce yourself and you can continue with your presentation. Thank you so much for accepting our invitation to present in this event.
May I?
Yes, go ahead.
Okay, thank you. Thank you very much again, Roberto, for this kind invitation to this very interesting conference. Interesting topics, very competent speakers, and a very good organization. I will talk about a topic that I've been working on since several years, and together with my colleagues from the geomorphology group of the Italian National Research Council Research Institute for Geological Protection, based in Perugia, and in particular, let me talk my colleagues Maria Teresa Brunetti, Massimo Medillo, and Silvia Peruccacci, because most of the work you are going to see we have done together. Just a brief introduction. We already know everything. Landslides are very different phenomena. Natural induced, human induced, of different types, different size, different depth, different movement, different velocity. And for this high variability, the landslides are very difficult to be predicted. Most of the landslides are induced by rainfall, and in some cases, just one meteorological event can cause up to several thousand landslides. Also, in a very few in a very few time. This is a case study we addressed with my colleagues here in Perugia of an extraordinary rainfall event that occurred in September 2022 in central Italy, and an extraordinary rainfall event with a V-shaped convective system with a peak of measured rainfall of more than 400 millimeters in 9 hours recorded by a rain gauge. This event triggered so many landslides, and we manually mapped into the field more than 1,700 in a relatively small area. This is to say that to predict rainfall-induced landslide and mostly work at a regional scale, we need accurate landscape information, accurate rainfall measurements, objective and reproducible approaches, uncertainty evaluation of such approaches, and also validation of such methods. First of all, collecting accurate landscape information. This is a crucial action for landscape prediction and forecasting. And for this action, we need standardized methods and accurate information. But we have to be aware that information on landslides is often difficult to retrieve and not fully reliable in terms of completeness and temporal and spatial accuracy. We addressed this topic here in my institute, and defining and then using a rigorous approach, we have compiled a catalog named Italica, the Italian rainfall-induced landslide catalog, which lists more than 6,000 records of information of rainfall-induced landslides occurred in Italy. We searched the information mostly on national, regional, and local newspapers, on blogs and online sources, on technical reports from, as an example, fire brigades, and also Italian railway network, Italian railway network company, the company that managed the network. And we also use an automatic search on the internet, combining different terms related to weather conditions and landslides in using Google Alerts. And after a long search with so many years of work, we collected this data. And for each information collected in our catalog, we stored an ID for sure, a bibliographic reference, an information source, type of the landslides, and accurate geographical and temporal information, longitude, latitude, day, month, and year, and time of occurrence. All the landslides are mapped as points, and with an associated geographic accuracy. Indeed, we assigned to each record a geographic accuracy class based on the area over which the landslide realistically occurred. So we passed from a very high accuracy when we know exactly the landslide location to a high accuracy when we know the location with an approximation lower than 1 square kilometer, and then medium, low, and very low. But the lower cases are represented in very few points. Also, we consider the temporal accuracy. We have so many landslides for which we know the time of occurrence, hour and minutes. Then for some landslides, we know just the part of the day, and for some landslide, we know just the day of occurrence. We discarded all the information in which we were not able to define the day of occurrence of the landslide. And after this work, we have now this catalog, more than 6,300 records of rainfall-induced landslide occurred in Italy between 1996 to 2021. This is overall the geographical distribution, with some regions with more information than others, also thanks to some agreements we had, and we are having with some regional administration. Looking at the geographical and temporal accuracy, we can say that for like 20% of the catalog, we know exactly the coordinates of the landslide. For half of the catalog, we know the location of the landslide with an uncertainty lower than 1 square kilometer, and go on. The temporal accuracy also is very high, because for half of the catalog, we know exactly the time of occurrence. For 1 quarter, we know just a part of the day, and for another quarter, we know only the day. And looking at that graphs, temporal graphs, we can see that both geographic and temporal accuracy have improved over time, thanks to also an improvement in the quality of information sources, but also in more, say, accurate work by all the operators that have done this work. This catalog is freely downloadable. This is I'm going to show you, this is a data description paper published in Earth System Science Data. You can download with this QR code, and you can download the whole catalog from Zenodo with all the information I've told you now. Freely downloadable, and we are very happy if anyone can use this data set for any kind of application. At the beginning, I said we need accurate landscape information, but we need also accurate rainfall information. And in Italy, we have a very good network from the Italian National Civil Protection Department, but we also have some regional networks. And thanks to several agreements from my institute to all these institutions, we can rely now on more than 4,000 rain gauges, well distributed all over the Italian territory, and providing rainfall data with hourly or sub-hourly time resolution. After we collect Landscape information, rainfall measurement with a very good accuracy, we need to define objective and reproducible approaches for defining any kind of prediction tool. So if we are using rain gauges, we need to define a rain gauge representative for any landslide point we have in our catalog, and so this is and also this process should be objective and reproducible. And also the rainfall event reconstruction should be objective and reproducible with some parameterization and some rigorous procedure. And also the definition of any prediction model, as an example, rainfall threshold should be objective and reproducible. In this case, let me show you very briefly the method we are using here, and it was also previously defined by my colleagues in my group. This is the frequentist method that is based on power law equation linking cumulated rainfall and rainfall duration of all the rainfall conditions that were defined in an objective way and were considered likely responsible for the landslide in a given area. Once we draw these points in a log plane, we can draw the best fit line, and so we can calculate the differences between the empirical value of accumulated rainfall and the modeled values of the cumulated rainfall given by the best fit, that is a line in a log plane, but is a power law function. Once modeling these differences, after modeling these differences with a kernel density approach, we can also apply a statistic model, as an example, a Gaussian function. And in this way, we have the distribution of such differences, and so we can calculate thresholds of different non-exceedance probabilities at any percentile, just by simply shifting the best fit line by a quantity equal to the differences between the median and the percentile in the Gaussian curve. As an example, the 5% threshold leaves below itself 5% of the empirical point with which it was defined. We also evaluated the uncertainty related to these parameters, and so we provide not only a simple equation, and not only a simple line, a simple curve, but a range of variation of the threshold. And this is very important, and we evaluated that such uncertainty range, uncertainty area, is linked to the size of the data set, and also the quality of the data set, but also is linked to the temporal resolution of the rainfall data used. And indeed, passing from hourly data to daily data, for example, we obtain a very significant increase in the threshold uncertainty. This procedure for threshold calculation, but also all the procedure for the objective definition of rainfall conditions likely responsible for landslide triggering, is now included in an automatic tool named Control T. Calculation of threshold for rainfall in this landslide tool is a tool is a code written in R, open source software, that needs in input just rain gauge data and landslide data. There is to say, it needs in input the location of the rain gauges and continuous rainfall measurements, preferably at the hourly resolution, and landslide data. There is to say landslide location, landslide time. This tool produces as an output all the rainfall events in a given area in a given time, rainfall condition responsible for landslide, and rainfall threshold. Also, this tool, which was mostly work by my colleague Massimo Melillo, is freely downloadable from Zenodo. The tool is mainly divided in three main logical blocks. The first one just need the rainfall data and allow the reconstruction of rainfall events by means of a rigorous and objective procedure. The tool needs in input a couple of parameters, that is to say the length of a dry period needed to separate two consecutive rainfall events, and also the definition of the length of the seasons, dry and wet seasons in a given area, in order to vary the length of the dry period. And after this, the tool can produce in output all the rainfall events from all the rainfall series. And the second block use also the information for related to the landslide location and days of occurrence in order to select first a rain gauge representative for the landslides, and then all the rainfall condition responsible for the landslide. And the final block allows the calculation of the rainfall thresholds. This is a case study we did in Italy, using only a part of the catalog that I showed you before. So we calculated different thresholds, different non-exceeding probabilities, and also we calculate thresholds not only for the whole Italian territory, but for several subdivisions of the Italian territory: a physiographical subdivision, lithological subdivision. We also considered soil, land cover, climate, meteorology, that means mean annual rainfall, in order to investigate how all such environmental factors can influence the triggering conditions for rainfall-induced landslides, and also how the thresholds vary in different environmental subdivisions. An interesting result was obtained for the threshold for different meteorological domains. Calculating the threshold for all the points located in areas with different mean annual rainfall, we obtained that the thresholds for defined for area at increasing mean annual rainfall were higher and steeper. So this means that the landscape adjusts to the meteorological conditions. So where a landscape that usually receives more rainfall during the year needs a higher and more intense rainfall event on average to trigger a landslide. And this is also another important consequence, because we have to be aware that where meteorological regimes will change, also in response to, particularly in response to global warming, all the predicting tools and systems need to be adjusted and adapted to such changes. And this result gives me the opportunity to talk about another application I did, as always in Italy, but only considering a region in southern Italy, Calabria region, where I come from, and using a long-term catalog of landslides dated back from 1921 to 2010, so a 90-year period of information. And daily data in this case, I reconstructed around 1,500 rainfall events with landslide during the whole 90-year periods. And I evaluated the changes in the triggering condition, but also in the spatial and temporal distribution of such events, of such rainfall-induced landslide in the three 30-year periods: 1921, 1950, 1951, 1980, 1981, 2010. What was found was very interesting, because it was found changes in the spatial distribution of the landslide in the three 30-year periods, a change mostly in the last two, because it was the two periods with more data. a change in the monthly distribution of the rainfall events with landslide, and also a change in the triggering condition. Indeed, the triggering conditions were calculated by means of rainfall thresholds, and what we observed was that there was a change in the rainfall thresholds. This change was observed both considering only the events occurred in the 30-year periods, so 1921, 1950, 1951, 1980, 1981, 2010, but also considering a moving window of 30 years by a step of 5 years. So allowing a more continuous evaluation of such changes. And what we found was a rotation of the threshold, and so changes in the triggering conditions of such phenomena in response to a change in meteorological features, and so in climatic, given the long-term evaluation of such changes, so we can say given to an observed change in climate in that region. And after that, I can conclude my talk, just summarizing some challenges that I think we can address in some way. First, I have talked about empirical regional scale approach, and I think that such approaches can be applied to different study areas where similar data is available in order to have a quantitative comparison of the results. And anyway, and moreover, empirical and regional scale approaches can be also combined with climate modeling chain, so with a climate projections to evaluate both changes in the past and in the future. This tool, empirical thresholds, can be considered a simple model, but it needs a rigorous and objective and reproducible theoretical basis and an accurate data set to be defined. And I think is a very useful tool to predict rainfall-induced landslide. For sure, the robustness of the thresholds depends on the empirical data set, and the robustness of the thresholds should be evaluated by means of a validation against an independent data set, that can be considered an independent data set both in time or a data set that were collected from different sources, for example. And moreover, also the uncertainty of such tools should be always evaluated and quantified. In conclusion, we can say that the prediction of rainfall-induced landslide in this changing climate that we are living, changing world that we are living in, is possible, and for sure can contribute to mitigate landslide risk. For sure, climate change makes the prediction more challenging, and for this reason, we need the rigorous approaches based on accurate and complete landslide records, as I think the one that I show you, so collected with standardized and rigorous procedures. We need also accurate and complete rainfall and climatic data, rigorous tools again, in order to reduce the uncertainties and provide reliable results. And with this, I've concluded my talk, and I want again to thank you for your attention and Roberto for this kind invitation.
Thank you so much, Dr. Stefano. These are topics that are fascinating to me, and thank you for preparing such an excellent presentation, sharing it with us. You have the title. We will also include the DOI and if other information about the research of the authors in the videos when we publish the videos, individual videos in the YouTube channel. I am taking a look at the live chat. Maybe if there are questions or comments. We have some minutes to address any comments.
Anyone, and in any case, if someone wants to reach me out or to contact me, here is my email address, and anyone can find also me on LinkedIn. And so I'm very happy to discuss about these topics with different ideas and perspectives.
Thank you. That's great, and that is also great to know for other researchers like me that are very interested in this topic. So thank you again, and I hope to see you in future events and that your future research may also be published and shared with the scientific community and the public in general. Thank you so much.
Thank you very much.
So thank you. We are back, and I am honored to introduce our next speaker. And I'm just going to allow or invite all those who are attending in, via YouTube. You can write in the live chat questions, whatever you want, or comments about the presentation. We are here reading all the comments or questions, and we are going to let the speaker know if there are questions. So I am very happy. Thank you, Dr. Sergio Arbana. Thank you for accepting our direct invitation to be speaker at the Landslide Scientific Assessment Conference. How are you?
Fine, fine. It is fine. Thank you for your kind invitation, and I'm very glad to be here.
Thank you. That's great. Feel free to present all what you prepared. Before, I am going to ask you to introduce yourself. Maybe let us know briefly about your research, and then you can continue. Thank you.
Okay, thank you. So you can see here that my name is Željko Arbanas. I am professor at University of Rijeka, Faculty of Civil Engineering in Croatia. And here I will present with some results of our project related to landslide initiation in small-scale slopes exposed to artificial rain. But you will see in my presentation that this is just a part of our results. And I have to say that we have so many data, very valuable data about landslide initiation in small-scale landslide models. And if there is someone who wants to cooperate and to analyze this data with us, all are very, very welcome. So we conducted a 4-year research project, and the title of project was Physical Modeling of Landslide Remediation Construction Behavior under Static and Seismic Action. And this project was funded by Croatian Science Foundation, started in October 2018 and completed 2 years ago. And it was completely conducted at the Faculty of Civil Engineering, University of Rijeka. And the main aims of the project are modeling and behavior analysis of landslide remedial construction in physical models of scaled landslide in static, that mean rainfall-induced landslide, and seismic, or better to say, earthquake-induced landslide conditions. And here you can see our schematic models. The upper one is a model that we use for rainfall-induced landslide models, and on the bottom you can see this model for earthquake-induced landslide. So at this full model on the top, we apply artificial rain by 3 sprinkler branches, and this is in this case it is possible to model different rainfall events until the landslide was activated in the slope. In the bottom, you can see that we have a platform. Also, we put this platform at the shaking tables. It is a pair of shaking tables, relatively very small, and we also apply different rainfall conditioning. It wasn't necessary to have rainfall and earthquake in the same moment, but it is very important to have moisture of the model that was relatively very close to the rainfall events that can be that can be done in the moment of rainfall. Here you can see our real platform, our laboratory. It is 2.3 meters long, 1 meter wide, and we put inside about 30 centimeters of material, of slope material. Construction of slope material was in 5 layers of material compacted with laths under compaction method, and each layer was of about 6 centimeters. If we are talking about this smaller platform, it is only 1 meter by half meter by 15 centimeters, 12 to 15 centimeters of material depth, because we were limited with the capacity of platforms, shaking platforms that is of about 130 kilos, and it is a problem because we in this case had a very, very small slope model. And here you can see the main part of our investigation. You can see medial measure that we used and that we applied in our platforms. From top to the bottom, we have firstly gravity wall, and on the left side, on the left column, you can see initial condition of the platform, and on the right side, you can see end of the test. And in the second row, you can see gabion wall, and in the third row, you can see pile wall. And we tested all this construction in different conditions. What was equipment that we used in this model? First, we have tensiometers that we put inside the slope, pore pressures, transducers, strain gauges, accelerometers. Then we have rainfall simulator. As I said before, it was one sprinkler system, and it was constructed of 3 branches. You can see here 4 branches, but we used only 3 branches, one in the upper part of the model, one in the middle part, and one in the top of the model. And each, you can see here is this photo of the model in the laboratory prepared for testing, and here you can see nozzles at each branch. We had 4 different nozzles for different intensities of rainfall. We also had high-speed cameras. You can see here. It is a pair of high-speed cameras that can use that we can take about 5,000 photos per second. But in case of this type of landslide, it is relatively slow landslide. We need, of course, very, very low frequency of taking photo. We also used terrestrial laser scanner at the start, at the end of the test, because we need about 20 minutes to capture the model with terrestrial laser scanner. And also we used infrared camera. It was used some tests, but we didn't have so good results using this. What are the conditions of the model? We use 3 different types of material: sandy material, 0 to 1 millimeters, then sandy material with 10% of kaolin, then sandy material with 15% of kaolin. And it's possible to use different slope inclination. We used 30, 35, and 40 degrees. And we also used different initial moisture, different rainfall intensity and different rainfall events. And here you can see grain size distribution curves for all three materials. I put these two materials in red because in my presentation I will present results using this type of materials, and also all results are related to 35 degrees of slope inclination. You can see that we have very small differences in grain size distribution when we add 10 or 15% of kaolin. But for these materials, we have a completely different behavior of slope. So you can see that when we add 10 and 15% of kaolin, we after that can obtain cohesion from 3.9 to 4.4 kilopascal, and you can see that we have some very important factors like hydraulic conductivity different from initial basic material. Here in this table you can see all properties of this material that we used in the models. Here is also one interesting element. It is initial water content. We use 2, 5, and 8.1% of water. It was important because before we started to construct the slope, we used these materials and we put in proctor tests to obtain optimal moisture for optimal construction of the slope, and this is the main reason why we use different initial conditions. And I will talk in my presentation about these two materials, sand and mixture of sand with 15% of kaolin. And the most important part of small-scale landslide modeling, and of course for any small-scale modeling, are similarity laws. So here is a very complicated situation to obtain similarity between a real landslide or real slope with this small-scale slope. And we can talk about three groups of similarities. First is geometric similarity, and then is kinematic similarity, and the third group is dynamic similarity. And when we consider what we can put in this group of similarities, here in geometric similarity we have model images, slope inclination, grain size distribution, moisture content, volumetric characteristic. In kinematic similarity we have sliding velocity, sliding acceleration, waterfall velocity, waterfall acceleration, rainfall intensity, infiltration, displacement. And in dynamic similarity, soil weight, strength parameters, soil suction, active forces, resistant forces. But we have impact between these groups, and some parts of geometric similarity have impacts to kinematic similarity and dynamic similarity. And we also have impact from some elements of kinematic similarity to dynamic similarity, like as you can see here, infiltration has impact to soil weight, to soil suction, to active forces, to resistant forces. And also inside this group, sliding velocity has impact to displacement, of course. Waterfall velocity have impact to displacement. And of course, we have opposite interaction, and so suction has an impact to waterfall velocity. A resistant force has an impact to displacement, and so on and so on. And of course, inside the group of dynamic similarity, we have also some impacts. And it is very complicated situation. If you change any part of the model, you can have so many impacts to some other similarity. And regarding this, we can conclude that landslide is a complex geomorphological process if considering all the factors that should be taken into account when modeling a real landslide. And it is clear that the landslide process is too complex for all elements to be covered by similarity laws to fully describe the mechanism, initiation, and run-off process of a landslide. So the simulation of a real landslide in a small-scale landslide model must be limited to the application of the most important elements affecting the landslide process, while all other elements should be adjusted just to imitate a real process of sliding. And of course, we cannot consider all similarity laws. We should take only the most important parts of the process and analyze results only for this. Here you can see application of rainfall, artificial rainfall to our two models. We can see that we have different intensity of 72.6 millimeters of sandy slope per hour and 22.3 millimeters per hour for sandy kaolin slope. It is to avoid surface outflow, and intensities were adjusted to infiltration capacity of the slope material. Infiltration capacity for both material are much higher, but if we would apply higher values of intensity, rainfall intensity, it is problem with erosion process with surface outflow. And here on this diagram, you can see the process that we have during artificial rainfall. Here you can see position of the first crack that occurred on the slope, and you can see that we started with intensity from the start to the one point. This point and also this point in the second test were the points when the toe of slope was submerged, and in this moment we exclude branch in the bottom of slope because it was not so important for other part of the process. And at the end of each process, each test, we open all nozzles and start to apply the maximum intensity of rainfall just to see what will be after that. And here you can see development of the process in the sandy slope. The first crack occurred after 62 minutes, and after 130 minutes we had development of retrogressive landslide to the top of the slope. And here you can see on these photos the process of this development of landslide to the top of the slope. And here we can see the movie. It is the movie that covers about 3 hours of the process of sliding in the slope, and this movie was constructed from the stereo pair of cameras, and it enables us to reconstruct the process. Right again. You can see that the process was started in the moment when the water in the lower part of the slope was covered the material in the top. So this is the end of the process. And here we can see the process in the sandy kaolin slope, and the first crack occurred after 35 minutes, and development of the landslide was in the other 65 minutes to the 100 minutes to the top of the slope. The first crack occurred in the middle part, of the slope, but without significant movements in the slope. And the groundwater reached the slope surface in the middle part, you can see here, forming small springs and surface flows and also erosion process. And we can say that it is joint mechanism of sliding and surface erosion, started with relatively fast retrograde stability development up to the slope. And here you can see developing of a landslide to the top. Here you can see a location of our sensors. We use 3 contour profiles. One, the lower part, in the lower part of the slope, in the middle part of the slope, and the last one in the upper high part of the slope. And we put sensors at different depths at 6, 12, 18, and 24 centimeters from the surface, 0 material in the slope. And we measured volumetric water content with sensor TEROS-10, pore pressure with TEROS-31, negative pore pressure but at the same matrix suction with TEROS-21 and 31. And here we can see results of this first. In the first row we have result for sandy material, and it is real. And from this result, we can identify volumetric water content in any moment of the test, and also for water pressure. It was a problem because when we started with first test, we didn't have sensors TEROS-31, and it was not possible to measure soil suction that we have in the second test. And here is the process explanation. In the sandy slope with relatively high hydraulic conductivity, the volumetric water content increased due to infiltration until saturation in the deepest part of the slope, forming the water table. When it is established, the flow down the slope started, causing rapid rise in the groundwater level in the lower part of the slope, and this led to decrease in the soil shear strength, with complete loss of the matrix action, failure, and further retrogressive landslide development to the top of the slope. In the slopes made of sand-kaolin mixture with significantly lower hydraulic conductivity, the process of saturation occurred first in the surface layer. That caused an increase of the weight of surface layers, causing cracks and shallow instabilities in the middle part of the slope without significant movements. The opening of the cracks allowed the water to penetrate in deeper layers and form separated saturated zones in the slope. And in some isolated local zones near existing cracks, the groundwater level rises to the surface, causing springs, pools, and erosion process. And for conclusion, we can say that landslide modeling in small-scale slopes exposed to artificial rain in 1G conditions is a complex process which requires a good knowledge of the behavior of the built-up soil material. The relatively small variation in applied soil material can lead to completely different instability mechanism processes. The leading parameters that remain stability in small-scale slope models at low confining stresses in 1G conditions are matrix action and cohesion. Application of model results to real slopes is very demanding process that should include numerous elements in geometric, kinematic, and dynamic similarity laws that are interconnected and mutually dependent. And at the end, I will present you just some photos when we use remedial measures and the slopes, just to see results of this, but without any numerical value explanation. You can see that we prepared this gravity wall using 3D printer, and it was in a scale 1 to 20 to some real gravity wall of 5 meters. We had excavation of foundation pit. Then we put wall behind it. We prepared geotextile to separate coarse material that we put behind the wall. Here you can see also sensors that we put in the wall, and we compacted this material, and we prepared slope with this. You can see here that we have stairs in a slope that enable better stability of this, and here is slope prepared for test. And after that, we applied rainfall. Here you can see at the moment when the toe was submerged with material, and when the started initial crack, it was in the upper part of the slope, but not in the middle part. Here you can see the end of the test, and from this picture you can see that the wall remained stable, but it was problem with some deformation. You can see it is not in a line. We have some movement here in the middle part of the slope, and also we have activation of the passive zone in the front of retaining wall foundation. Here is the preparation for gabion wall. You can see one element of our gabion wall. We had element 10 by 5 centimeters. Then we prepare foundation for this gabion wall, of course, coarser material. Then put some lines of gabion, or using a rule for arrangement of gabion as we used in the real construction site. We also put some material, coarser material, behind the wall. It is also separated from the floor material with the geotextile. Here you can see additional zone, preparation of stairs, and finally prepared model for testing. Then we applied rainfall, and here you can see some results. After that, we have some small cracks here, but the main crack occurs also on the top of the slope. We also have the same problem with this material, because here occur some type of spring because of rise of groundwater in the surface layer of this silt, some coloring material, and here you can see results to the end of the test. And this is the third test with pile wall. We prepared the foundation beam. It is not real in the practice, but it wasn't possible to obtain good foundation for this. Then we put piles, also prepared with 3D printer. Then we put material behind and in the front. Then we prepare some buttressing material in front of pile. It was also separated with geotextile. Then we put prepare drains behind the wall construction. Then we put head beam to connect all piles in one in one pile wall, and here you can see the model prepared for testing. Then we apply the rain, and here you can see development of landslide, but on the top of the slope, the pile wall remain stable to the end of the test, but when we apply high intensity, you can see that we have some erosion process, but without losing stability. And this is the end of the process when we stop the difficult rainfall. And this is the end of my presentation. As I said before, results were obtained from the project funded by Croatian Science Foundation, and some papers related to this you can find on this address. If you want to contact, here is my email address, and on the picture here you can see our truck sunk in the liquefaction that we obtained in a dynamic model and put on the shaking table. So this is my presentation. Thank you.
Thank you so much, Dr. Selko. This is very interesting. I invite all those who want to ask questions or directly contact, probably those who watch the video later as well. You can contact Dr. Arfana directly. And thank you so much for your presentation and what you prepared today.
Thank you. If there is any question, please send me by email or put in the chat. Thank you.
Thank you.
Ladies and gentlemen, today, I'm thrilled to present a systematic review from the esteemed journal Structure and Infrastructure Engineering, published by Taylor and Francis. This review not only delves into the captivating realm of geotechnical slopes but also sheds light on the development of crucial deterioration models. Authored by Roberto J., Marin and Michael Long, this paper highlights a vital aspect of infrastructure management, the often overlooked deterioration of earthwork assets. Why does this research matter, you ask? Geotechnical slopes, like embankments and cut slopes, form the backbone of our infrastructure networks, supporting roads, railways, and various civil engineering projects. However, as time passes, these slopes undergo deterioration due to various factors, including weathering, erosion, and human activities. Understanding their long-term behavior is paramount for effective asset management, ensuring safety, minimizing costs, and maintaining operational efficiency. The systematic review endeavors to answer key questions by exploring existing deterioration models for geotechnical slopes, analyzing methodologies, monitoring techniques, and data collection approaches used over time. It consolidates knowledge from scientific literature, identifying gaps and limitations in current research while emphasizing the importance of proactive maintenance and predictive capabilities in infrastructure management. One notable revelation from the review is the scarcity of comprehensive deterioration models specifically tailored for earthwork slopes. Despite growing interest in the field and an increasing number of research papers addressing the topic, robust models remain elusive. However, the review uncovers a wealth of studies focusing on factors and mechanisms contributing to our understanding of long-term asset behavior. These studies, although not explicitly addressing deterioration models, offer valuable insights for future model development. Moreover, the review emphasizes the significance of monitoring, instrumentation, and data collection in enhancing our understanding of geotechnical asset deterioration. It proposes a framework for long-term analysis, advocating for a combination of lab.
Welcome back. We are just waiting because next presentation was about sensing technologies for landslide monitoring. And I'm not sure if something occurred with the speaker, but I want to just say again what I said some hours ago. We had one presentation yesterday, day 2 of the Landslide Scientific Assessment Conference that did not or had some technical issues, and then we just uploaded the full video in good quality of that presentation by Dr. Susana Pereira to the LandScient channel. Maybe we can play this presentation during this time if we don't have the speaker scheduled at this time yet. Very briefly about you or your research, and you can continue with your presentation. Thank you.
Okay. Hello, I'm Susana Pereira. I'm an assistant professor at the University of Porto in the Geography department. And today I will present some results of a previous research project funded by the National Portuguese Science Foundation for Science and Technology. And the title of this work is a landslide risk index for municipal land use planning in Portugal. This was a project of 3 years of research, and I have more colleagues that participated here in this study that are listed here. To begin, to start this presentation, I would like to say that in Portugal, in the last 150 years, landslides caused 237 fatalities and more than 1,600 displaced people. And the spatial distribution and temporal patterns of these landslides can be related with some a complex set of natural factors and also human factors responsible for generating damages. In this context, it is important to develop some methodologies to synthesize risk dimensions and to contribute to risk management. As we can see here in this picture, we have the spatial distribution of the landslide disaster cases and also the information about the elevation of the country, where the steepest areas and the mountain areas are located in the northern sector and also in the center of the country. And these areas are the most prone to landslides. Also, we have some cases of landslides near the Lisbon metropolitan area. And these cases are responsible for a large set of landslide fatalities and also displaced people, as we can see here, where we have two main spots of damages caused by landslides, here in the Lisbon metropolitan area and here in the Oporto metropolitan area, where we have more population and also activities located in hazardous areas. Also, we have some cases of fatalities widespread in the northern area, most of them related with railroads and roads that were affected by landslides and caused fatalities. So in this context, we had published a database of these landslide disaster cases for the period between 1865 and 215, which was updated until 2020 and is available at the Zenodo platform if you want to download and check the data. In this context, the main objectives of this study are to assess the landslide risk using a data set of variables to characterize risk dimensions, for instance, hazard, exposure, and physical vulnerability of buildings. And we'll use normalized and weighted variables to compute a landslide risk index that will be represented at the municipal territorial unit. The second objective is to perform a cluster analysis to rank the municipal landslide risk in order to identify landslide risk profiles for different groups of municipalities and also to contribute to the identification of different measures adapted to the risk profile of each municipality. When you go to data and methods, we used an adaptation formula of the risk of the informed methodology. Our landslide risk index results from the multiplication of the hazard, exposure, and physical vulnerability of buildings represented at the municipal terrain unit, and the landslide risk dimensions, for instance, hazard, used some variables to assess hazards at the municipal level, for instance, an index that represents weather and climate events that caused disastrous landslides in the past, and also the identification of the most susceptible areas of the country using a bivariate statistical model, the information value. About the exposure, we used information from the Portuguese census of the population from 2010, and in order to obtain information about the population density and the number of buildings. Additionally, in order to estimate the physical vulnerability of buildings, we used the georeference base of buildings of the country, which all the constructed buildings with residential function are located. And then we have some details about these buildings. For instance, the construction technique and construction materials, the building structure, the number of floors, and also the conservation status of those buildings. And so we have this information for the complete country. When we start looking to the hazard and how we did obtain the hazard at the municipal level. We started with the landslide susceptibility map that was obtained from a national landslide susceptibility model. This model used a geomorphological landslide inventory with more than 7,000 landslides widespread in the country, located in some sample areas where we performed field work and photo interpretation, and we were able to identify more than 7,000 landslides. And at the same time, in these 14 selected study areas, we believe that they are representative of the country geology, diversity, and also the geomorphology, the diversity of the country. So we used this inventory based on photo interpretation and field work, where we know that the temporal resolution is low. Most of the times we do not know the dates of the occurrence of these landslides, but the spatial resolution is very, very good because we know the location, and so we can assess the predisposing factors associated with these landslides location. And this inventory corresponds more or less, includes more or less landslides for the period starting in 1950 until 2015. Then we used a set of 7 landslide predisposing factors with a raster data structure with 25 per 25 meters resolution, and we consider the elevation, the slope angle, the topographic position index, the lithology, the soil type, ecological units, and water availability in the country. And then the next step was to perform the bivariate statistical model, the information value method that is represented here with this formula, in order to identify the most susceptible areas in the country. In this case, the areas with the positive information value scores were selected from the landslide susceptibility model and were isolated the most unstable areas of the country, okay? And then the percentage of the municipality area with a positive information value score was computed for each municipality in order to obtain the most susceptible area for each municipality. I forgot to say that this landslide susceptibility model was validation using success and prediction rate curves, comparing with the different landslide inventories. And in this case, the success rate of the model that used more than 7,000 landslides was 0.94. So we are very confident with the results of this model in this case, as I said here. And then in the end, the areas with positive information value scores were selected from the landslide susceptibility map, were isolated, and then we computed the most susceptible area for each municipality, and then this information was normalized between a range in the interval between 0 and 1, just like that, in order to identify the most susceptible landslides in the country, most susceptible municipalities in the country. In order to obtain the landslide hazard, we needed a temporal dimension of the landslide triggering, and again represented at the municipal level. And our choice was to perform and to compute a weather and climate event index. And in order to compute this index, we performed a statistical study in order to know the most frequent circulation weather patterns associated with landslide disaster events. We have published this work previously, and we concluded that the landslide disaster events usually are associated with southwestern patterns, western patterns, and also cyclonic patterns, which can be represented at the municipal scale. And also we computed an extreme precipitation susceptibility index that considered high intensity rainfall events. And in this case, we performed a weighting of these parameters, a multi-criteria weighting. And in order to obtain this index of weather and climate events. Again, this weather and climate index is a proxy for the temporal dimension of the hazards and was computed using the equation proposed by Santos et al. And the results were further normalized again to the interval between 0 and 1. And then we obtained the municipalities where the triggering conditions are more frequent to obtain disastrous landslides. Again, in order to obtain landslide hazard, we combined landslide susceptibility and landslide and weather and climate events responsible for the landslides, attributing more weight to the susceptible conditions because the predisposing factors that we found in the territory have more control in the landslide location. And then we obtained the hazard representation at the municipal level, again, normalized in order to be compared with other indexes. About the exposure, the exercise was very, very simple. We used the population density at the municipal level and also the number of buildings, because the spatial distribution of landslide losses shows that landslides occur in areas with the highest population density along transportation corridors and in buildings. So the most exposed areas are located inside buildings and along transportation lines. More than 50% of the landslide fatalities occurring in the period between 1865 to 2010 and occurred inside buildings. This is why we only use the buildings. The exposure dimension considers the population density, number of inhabitants per square kilometer in each municipality, and also the number of buildings in each municipality. Both of the variables were obtained from the population census in 2011, and we attributed the same weight for each variable in order to obtain the exposure index in the country where it has a different spatial distribution, very influenced by the location of the main cities and the main infrastructures of the country. Finally, the physical vulnerability, again, we selected the buildings. Here, the physical vulnerability of the built environment is the degree of loss due to landslides, expressed on a range from 0, no loss, to 1, total loss. We considered 4 building features: the construction materials, the reinforced structure, number of floors, and conservation status in order to obtain this vulnerability index. For each building feature, we selected a list of building feature classes, and we for each building class, each building feature class, we attributed a vulnerability score that were attributed based on an empirical weight, based on our field experience, and in the end, the results are consistent with the building's construction quality along the country and with the landslide damages reported in the landslide database for more than 1 century. So the result of this weighting, of course, in the end, we attributed a score for each building feature according to some references and some previous studies. that you can see in the final publication of this study. And then the final result was this, representing the.
So we are back. I am with Dr. Javier Rabel. Thank you so much for accepting our invitation, direct invitation to present that at this event. Please, it is your time. Maybe you can introduce yourself before you start with your material. And thank you again for accepting the invitation.
Thank you. Thank you for the introduction. And well, the pleasure is mine. It's a shared pleasure, let's say. As we have probably a worldwide audience, I will say good morning, good afternoon, good evening, so that, to make sure that everybody is greeted correctly. And well, I'm going to talk about sensing technologies, and it will be more like experience sharing with two types of technologies. One is optical fiber sensing, and the other one is wireless sensing using MEMS, so electronic microsystem. And let's say I will start the presentation by a quick introduction, giving you some motivation for why we do that. We will then see some details about optical fiber sensing. So I will enter into the physical principle of that type of technology, and optical fiber technology is multiple. You have many type of sensors. So I'll be focusing only on what we call distributed sensors. And and why is that? It's because they can take advantage of the existing transportation infrastructures. And then we will move to the next part of the presentation, let's say the second part, which is the wireless sensing technology. And we will see that here it's probably more appropriate for local monitoring, so a specific landslide, not a complete infrastructure. And the good thing, the interesting thing is that it's totally, it has very low environmental impact. And of course, I will not end my presentation without the conclusions. Okay, so let's start. And let's talk first about optical fiber sensing. And when we talk about optical fiber sensing and distributed sensing, very often we are talking about transportation infrastructures. So transportation infrastructures are pipeline, highways, railways, power lines and cables, waterways, any linear long distance structure that is used for basically communication of people, product, energy, and so on. It's very common to have along this, provided that they are not too old, and it's very common to have optical fibers laid along this transportation infrastructures, because the optical fibers are used for communication. And well, they are also kind of linear infrastructure. So it's kind of matching between the two approaches. Communication. So people are using the optical fiber for their own communication, like a pipeline operator who use it for its internal communication, and also for its SCADA. But some of them are also using the optical fibers to lease this optical fiber. We could talk about dark fibers. So they are, let's say, making money also not only with transportation of the natural gas, for instance, but they are also making money with by leasing the optical fibers for bandwidth increase. The interesting thing is that if we know about the physics in optical fibers, it's possible to turn them into strain, temperature, and vibration sensors. And what is even more interesting is that you can make the sensors continuous. So that's why we talk about distributed measurement or distributed sensing, meaning that we have along the optical fiber thousand or hundreds of thousands of microphones, temperature, thermocouples, and strain gauges. I'm just an image, just to picture a little bit what I'm talking about. But it's really like having multiple sensors, or a sensor every 1 meter, but it's not a physical sensor attached to the fiber. No, it's the fiber itself that is the sensor. And then if we talk about wireless sensing, what is interesting is that you can have that kind of sensor laid in a landslide, because we cannot cover thousands of kilometers or hundreds of kilometers with that technology, but it can be a support of the optical fiber sensing technology to, let's say, focus specifically on a landslide threatening a pipeline or a highway. And that kind of sensor can be implemented, or let's say the radio communication used in wireless sensing can be used to connect strain gauges, inclinometers, piezometers, and seismic sensors. What we will focus on here is on seismic sensors. So let's start by with optical fibers, and I cannot resist the pleasure of talking about physics. Being a physicist myself, I'm not a geotechnical engineer nor a geophysicist. I'm pure physicist with optical fiber and optical sensing background. And let's say, if we talk about optical fibers, and the physical mechanism that's behind sensing is light scattering. And light scattering is natural. As soon as you have light, as soon as you have a medium, you will have scattering. There is no way to avoid it. And actually, light scattering for telecommunication is an impairment. But for sensing people, it's a very good friend. We will see why. And scattering, as I said, is natural because it comes from the inhomogeneities in silica, which can be static or dynamic, moving or vibrating. So, and scattering, as I said, is natural. So here is an example of a glass rod where we have a laser beam propagating. You can materialize the laser beam because you have scattering. You have a change in the density of the media. You have a more dense media, and then more scattering centers, and that provokes the scattering. So you can see the beam because you have a fraction of the light that is taken out from the propagation. And that's what we take advantage of in optical fiber sensing. So that kind of approach, that kind of physics is implemented in a technology called optical time domain reflectometer, where a pulse is launched into a fiber, and all along the fiber you have a fraction of the light that is scattered. And even a smaller fraction of that light is back scattered. So it goes in all directions, and a fraction of it is coming back. It's back scattered. So it's like a continuous reflection. So the signal is recorded by a detector, and we have a signal, and that is measuring, or an interrogator that is measuring a trace, which is a function of time, the time of flight of the pulse in the fiber. And we can convert the time of flight of the propagation into distance, so that we can locate events. We can tell where things are happening. Then, by analyzing the scattered light, we see that its spectrum is not just a single light component. It's not purely monochromatic. If we send a pulse, a monochromatic pulse, it will be scattered with several components. We have one component called relay, which is at the same wavelength as the input signal and as the input pulse. And then we have side peaks, which come from various origins. I'm not going to detail that here, but one is called Brillouin and the other one is Raman. And nature is beautiful because each of them has a potential application for sensing. So with railing, you can implement what we call a distributed acoustic system, or let's say a dynamic strain sensor. So we will capture changes in the amplitude and the phase of the signal, fast changes, and then we can then have a kind of vibration sensor. Raman, the intensity of the Raman lines is sensitive to temperature. So by measuring the amplitude variation, we have an information about the temperature of the fiber at that specific location. And the Brillouin line is also very interesting because it has a cross sensitivity to strain and temperature. But here we don't look at the amplitude variation, but we look at the change in the wavelength. And that change in wavelength is proportional to temperature and strain. Actually, it's the optical frequency, not the wavelength. So we have three techniques that can be used for fiber sensing. The only, let's say, the negative point, let's say, is that we cannot have just one unit, one interrogator that does everything, because the type of signal requires a very distinct optoelectronic to create the pulse, to generate the scattering, and to analyze the scattering, the light that's coming back. So we need three boxes, three interrogators. Now, from temperature and strain and dynamic strain measurement, we can extract interesting things. First, with strain measurement in the soil, we can measure or we can monitor subsidence and landslide. And using temperature, we can actually monitor erosion and eventually calculate what is the depth of cover. So what is the remaining soil, quantity of soil or depth that we have, the remaining quantity of soil that we have on top of the fiber. For strain sensing, we need a dedicated strain sensing fiber or cable. Eventually, we can imagine to have embedded in a communication cable strain sensing elements. Now, for optical fiber, for temperature, we can use a common optical fiber communication cable. And that kind of technology has been implemented in, several projects for now more than 15 years. And here is an example. It's a landslide that was detected in 2011 in Peru on the PLNG transport system. So it's natural gas transport system. And that's we could associate with that landslide two patterns. One spatial pattern, which is the strain versus distance, where we see the pattern developing over time. It increases, the intensity increases, and we also have an information about the width of the event. So we have information about the spatial extension of the landslide. Here we are talking about 35 meters. And on the top right figure graph, we have the temporal evolution of the peak value and let's say the neighboring let's say at rest section of the fiber. And so we can also monitor the velocity and how fast this landslide is developing. And that's captured and collected over time and sent to a server that can do analysis and generate alarm if it's let's say if it's configured for such functionality. Now, using, let's say, dynamic strain monitoring, and we can do, let's say, for instance, rockfall and avalanche detection. Here is an example where we did a trial that's in Switzerland, and we laid an optical fiber cable in the ground. It was buried as well. And we were measuring back and forth. So the fiber is looped back. And we generated an explosion nearby the cable. And we could capture two signatures, each of them corresponding at two different positions in the cable. And if we look at the specific position where we have the maximum intensity, and we see the waveform associated with the explosion. So we have like a damped harmonic oscillator curve showing the time evolution of the vibration and its attenuation after a certain time. So, for instance, that has a very, let's say, interesting application to detect rock falls on a highway or on a railway. If let's say, if optical fibers, of course, are laid in parallel to the structure, which is kind of for railways kind of very common, at least in Europe. Now, with an example here is, or two examples with the application of temperature sensing. So we see an example on the left of erosion that occurred after a heavy rainfall. So the soil was excavated by the water flowing, and we could see in the temporal pattern a drop in temperature and then a return to the ambient temperature in the ground. And that event has as well a spatial extension, as we can see, of a few meters. So as in the other two examples, we see that we can have an information on the position of the event and on the severity and on how it has evolved over time. On the right figure, on the right graphs, what we have here is another example that's again in Peru. And what we see is in the spatial pattern, we see three events with varying amplitude, time varying amplitude, that are kind of with distinct maximum. And if we look specifically to event one and compare the peak amplitude with the ambient temperature variation, we see that we have the same pattern. We have a 24 hours periodicity. So, but the difference here is that the amplitude is much lower, and also we have a phase difference, so a time delay. And actually, that's because here the fiber is not directly exposed, but it's still buried, but with less material on top of it. And by calculation, we can find that actually for that specific event, we have, so event one, we have, let's say, still like 10 to 15 centimeters on top of the cable. And the last one, what was remaining was 50 centimeters. And for event two, it was about 20, 25. So we have a technique here that can also detect the preliminary signs of a risk of exposure of the cable. And if we have a pipeline, then exposure of the pipeline. And of course, in any case, if we are along a highway or railway, it's also an indication of, let's say, a reduction of the material on top of the fiber, which can affect, of course, the infrastructure. Okay, so that's all about examples, all about distributed sensing and detection of natural hazards, and even, of course, landslide. So let's now move to the example of wireless sensing. And in this case, we have we are talking about a network of wireless sensors, which are actually accelerometers, and that has also a temperature sensor embedded. We can implement about 50 of them, and they communicate with a gateway. We can also use the same communication module, radio communication module, to connect piezometers, inclinometers, well, just any kind of geotechnical type of sensor, and that data can be also collected by the gateway. We can also have data coming from third party directly on the gateway, like from via Modbus from the SCADA, and this information are, let's say, transferred to the cloud, where we can do, let's say, create digital twins of the event we want to monitor. And we can also combine by opening via API, we can open door and synchronize database, collect data from also third party, like meteorological data, any kind of information that can be useful for modeling. And then depending on the type of event, we can create KPIs that will be that we will be using in a dashboard that can be where we can generate alarms. So this is, let's say, a bit the architecture that can be implemented. And as I said, here we have sensors that are synchronized. That's very important for seismic monitoring. Here is an example of an active seismic monitoring test we did. So we had a person hitting the ground with a hammer, hammering the ground, and what we see, each line corresponds to one impact. If we zoom in the impact, so just one impact, we see that it has a waveform. So it's a structure like the one we saw with the optical fiber. It's characterized by a period and a decay rate. So we can calculate this information and actually relate them to the spectrum of the complete trace here, and we see that actually the value that we get corresponds for the maximum correspond to the period here, and to for the decay rate to the amplitude, and it's just the inverse of the time parameter. And then we also have a second line, which is which is an harmonic of the central component. So we can do soil characterization and active seismic monitoring with that kind of sensors. Now there are other techniques that are using passive seismic monitoring, and for instance, provided that we have structures that are rigid, like rocks, rock pillars, or eventually bridges, tunnels, dams, concrete dams. And we can do a modal analysis and also extract information about the natural frequencies. And from this information, we can, it's possible to monitoring the change in the natural frequencies and the structure of the model, and the model structure, that there is a degradation in the structure. Now, if we are willing to monitor a landslide, because the structure, the material is more loose, then we will need to do seismic velocity analysis. But in any case, the idea here is to capture just ambient noise to monitor change in the structure of the object we are monitoring, And what is required is to have multiple sensors and being able to do synchronized captures. We need to have very low frequency capabilities, and basically 0.1 hertz is probably even not good enough. So, and we can go below 0.1 hertz. And of course, because we are talking about noise and capturing noise, generate ambient noise, we need very sensitive sensors. Now, here is an example of a work we started recently on a water reservoir in Sao Paulo area in Brazil. And we can see the capture. So we have implemented 7 sensors in the slope of the embankment on the top and some sensor at the bottom. And we were capturing events that are related to, let's say, cars passing by and, well, any source of noise in the area to perform this natural frequency monitoring. And a last example that is probably the most interesting of this presentation is the monitoring of a landslide in Switzerland. So they implemented in that specific landslide that was threatening a road here at the bottom. So they were monitoring the landslide using various using conventional instrumentation, static instrumentation, using doing electric profiling, using inclinometers, and also they were monitoring the ambient noise caused by the cars passing by. And they were doing that by using 2 seismic sensors that were located in the stable part of the landslide. So on the site, and they were, well, the distance between the 2 sensors is, if I remember correctly, 10 meters, about 10 meters, maybe a bit more. And in that specific case, capturing the passive seismic noise, they were cross-correlating the information between the two sensors, the waveform of the 2 sensors, and comparing the cross-correlation with a reference value. They were extracting the relative velocity variation, so normalized. And then we can see over time that while it's fairly stable until let's say end of July and in 2010, then they had a drop because it was associated, or at that specific day they had a very heavy rainfall, and then the relative velocity started to drop a little bit more. It was not as stable as before until it reaches a point where we had a very significant variation, decrease of about 7%. That was mid-August, and that was, let's say, associated with another heavy rainfall. And then a few days later, the slope collapsed. So they were using that kind of approach, so passive seismic interferometry, to extract, to evidence or to predict, let's say, well, the occurrence of a landslide. Well, prediction is probably not the right word, but let's say to detect the preliminary signs or signature, the preliminary signature of the event. Okay, so that last slide will leads us to the conclusion. So as I stated at the beginning of the presentation, this is really a discussion about some cases and how to, and we see that we have 2 complementary approaches. Optical fibers, you can use them if you have an existing infrastructure It's fairly simple. You just connect the right interrogator, you monitor temperature, strength, vibration, and then the connection is kind of a retrofit with very limited environmental impact. There is little excavation to be conducted, so just connect the equipment in a shelter and usually you have shelters for communication equipments. If you really want to have very accurate strain measurement, you may have to do some excavation, but you can take advantage of remediation work to install that specific cable and splice it to the communication cable. And the advantage is that when the equipment is connected, you can hook it to the communication network and take the data and do the analysis and eventually generate alarms when it's configured for such application. And really, we get a system that is monitoring permanently the infrastructure and detecting events that can threaten the infrastructure. The advantage, then if we want to have a more detailed, or understand better how a specific section of the infrastructure is let's say moving, we can do, let's say, more traditional implementation, so to monitor specifically the landslide. But again, if we use wireless sensing, we don't have to excavate for the cabling. We have batteries, wireless sensors with batteries. So then the sensors can be, so that the implementation, the installation would have also a very limited environmental impact. And you don't disturb the landslide too much. And for the data communication, eventually, if there is no optical fiber available or a terminal equipment where you can hook the gateway, you can communicate via 3G, 4G, or eventually satellite data communication network. And some of my partners they use Starlink and just to communicate the data. And of course, well, I have been talking a little bit more about the dynamic monitoring and the seismic monitoring, but you can, of course, use static devices such as inclinometers, piezometers, tilt meters, well, whatever you need to, whatever parameter you need to monitor. So, ladies and gentlemen, I'd like to thank you very much for your attention. I also would like to thank again LandScient and Roberto for putting together this event. And if you want to learn more and read more about what have been talking about, there are some of these references are kind of comprehensive and well detailed. So just feel free, and of course I'm available for questions. Thank you very much.
Thank you so much, Dr. Fabian. It was a wonderful, majestic presentation. I am very glad that you shared this very important perspective and very related in a practical way for solutions for our landslide problematic. And thank you for your kind words at the end as well. I hope that your research, your professional and practical work may be very successful as it has been. And thank you for showing us all this today.
Thank you. I don't know, is there a session for question or?
Yeah, there is. I just took a look at the chat. I am waiting to see if there is something to say. We are still short of time because next presentation is just about to start.
Oh,
but
okay.
feel free, all those who want to to in the via email or comments here to reach Dr. Fabian. Probably you will find answers from him.
Thank you.
And thank you. Hello, Dr. Dario. How are you?
Hi, fine. How are you?
Great to see you. I am very well, thank God.
Yeah, well, thank you.
And
Thank you. How are
thank you
you?
for.
Fine?
Yes, very good, very good. I'm very glad, also very happy to meet you now in
Yeah.
this event.
Me too, me too, me too, me too.
Can
Okay.
you prepare maybe open your screen to share the screen? We make the
Yeah.
arrangements for the.
Just a second.
So we continue with the Landslide Scientific Assessment Conference. I am very glad now I have the opportunity to introduce Dr. Dario Peduto. It is an honor for me, and I am very glad that you accepted our direct invitation to present today. How are you?
Yeah, fine, fine, fine. Thank you for inviting me. Thank you very much. Can you hear me? Yes, okay.
Thank you. Yes, I can hear you very well. It is your time, so go ahead. Maybe I have asked other speakers as well. Can you just briefly introduce yourself and you start with your presentation? Thank you.
Yeah. Okay, thank you. First of all, thank you to Roberto for inviting me here. I'm Dario Peduto from the Department of Civil Engineering of University of Salerno. I'm geotechnical engineering. My presentation will focus mostly on the multi-source database, the risk assessment of roads interacting with slow-moving landslide. This research has been carried out jointly by my research group from University of Salerno and two research centers from the National Research Center in Italy, from IREA in Naples and IRPI in Cosenza. So the topic will be the risk assessment for roads affected by slow-moving landslides. Slow-moving landslides are widespread in different geoenvironmental contexts all over the world. Usually, typical types of slow-moving landslide can be rotational translation slide, earth flow, soil creep, of course, and a combination of them in complex phenomena. They range from the slow to extremely slow types of awareness classification, can occur usually, at least in the environment that I'm going to talk about, in structurally complex formations, such as stiff clays, soft clays. And usually the landslides I will talk to you will be usually active landslide moving on existing sliding surfaces, which can be occasionally reactivated after a very heavy raining period. These landslides are slow, so let's say that they cannot threaten directly human life, but they can cause damage, let's say consequences to the built environment, such as for roads, for buildings, for all the assets. And when we talk about consequences, we are in the field of landslide risk framework. In this case, we can say that consequences can be the combination of the exposure and vulnerability. And usually the consequences are the outcome of the potential outcomes of the interaction of the given landslides with the environment, the built environment. Usually consequences entails the identification of the elements at risk and of the vulnerability. Elements at risk. The first group of things that we have to address are elements at risk, which can be identified over inventories, and most of all, according to the scale of the analysis, they can be derived. For instance, when we are talking about building, we can go from the aggregation of buildings when we move at small scale until, for instance, the single buildings when we reach the detailed scale. As for vulnerability of buildings and roads, in general, from the theory, vulnerability expresses the degree of loss of a given building or road when they mechanically interact with slow-moving landslides, in this case. And the vulnerability of the building, of the exposed road, can depend on the landslide type mechanism, of course, and its related intensity. The intensity of slow-moving landslides usually is associated with displacement or their velocity, but other influencing factor to the vulnerability can be also the location of the building or the road within the landslide body, or of course the structural characteristics, the construction characteristics of the road or the building. As for the intensity, when we talk about slow-moving landslides, generally in literature we are talking about displacement or even more sophisticated parameters such as differential settlements or angular distortions and so on. But usually this kind of data should be derived from conventional monitoring systems, but sometimes when we are working over large area, this information can be not affordable in terms of cost and for the surveys. So that today, luckily, we can say that there is another technique from remote sensing, such as the differential interferometry, that is the processing of images acquired by synthetic aperture radar, which can provide today displacement over large areas of the ground surface with millimeter accuracy on the velocity. This technique always provides displacement information on targets that can be identified with the roof of the buildings, or with the pipelines, bare rocks, and so on. That's why it has had huge exploitation in the last decades in the field of civil engineering. The study area. The study area that today I want to show you is located in southern Italy, specifically in Calabria region, and this area is a town. The town is the name is Acri, with 20,000 inhabitants. The area of interest is this green area that is a deep-seated gravitational slope deformation, on which the exposed element in which we are focusing our interest, the Statal Road 660, crosses for around approximately, let's say, 3 kilometers. The area is affected by widespread slow-moving landslides. Indeed, the geological, geoenvironmental environment context is made by high-grade metamorphic rock of phylogenetic age. These metamorphic rocks experienced, with passing of time, intense weathering processes, which resulted in complex and deep weathering profiles, along which especially the sliding surfaces occur. As you can see from the map here below on the left, there are several landslides affecting the area. Especially they belong to the type of slide, debris flows, debris slide, and rock slide. And they are overimposed on a deep-seated gravitational slope deformation that you can see here also in green. The area has been studied for a long time by the National Research Council in Calabria, in Cosenza. With passing of time, different type of monitoring has been installed in the area, starting from, of course, ground-based conventional monitoring, such as inclinometers, which concentrated especially here in these landslide that is zoomed here on the right. That is an active rotational rock slide, which reactivated in 1998-1999, and then after that all these studies started. Then this inclinometer monitoring was integrated by GPS monitoring. You can see here the triangles with the location of the GPS, and of course piezometers, and more recently, these information were integrated by SAR interferometry. Going to the description of these four maps, you can see on the left there is the database of permanent scatterers, which are points for which each of them we have displacement time series, and of course velocity. These points belongs the ones on the right, on the left belongs to the Sentinel sensor, covering a period from 2014 to 2021. Images were acquired on both orbit, ascending and descending. The first, the top, and the lower is descending. On the right, you can see instead Cosmos SkyMed images. Of course, you know that Sentinel images are acquired at C-band. Instead, the Cosmos SkyMed is acquired in X-band. That is much more fitting for this kind of application to the built environment. In fact, the Cosmos SkyMed images provided the maps of permanent scatter that you see here on the right. The points are located over, providing a good coverage on the road that you can see here in gray. And there is, of course, if you compare the left and the right maps, you can see that there is the density of the permanent scatter is much increased in Cosmos SkyMed images, which cover almost 11 years starting from 2011. The methodology, what we did, the analysis on the Acri case studies were carried out following this methodology, divided in 4 phases. In the first phase, the main goal was the landslide characterization of all the landslides in the area. This landslide characterization was achieved by combining background information consisting of geological, geomorphological features, geotechnical soil characterization, landslides inventory map, and of course the use of ground ground-based monitoring network. At this stage, an important step was the comparison of the remote sensing data with the ground-based monitoring in order to assess their reliability. And it was a kind of validation which allowed us to use also remote sensing where ground-based monitoring was not available. In the second phase, starting from the map, the landslide inventory map, by merging with the urbanized area map, we singled out the exposed elements. For these exposed elements, in this case, we focused mainly on the road crossing the landslides. And in this road, the damage assessment was carried out with the use of archive photos, which were available from the National Research Council, field survey. And as a novelty, also Google Street View imagery was used for assessing the damage. After the assessment, the damage was ranked in a damage ranking scale, which we properly defined for the case study. And this allowed us to arrive to a multi-temporal damage classification. The level of damage was then combined with the intensity parameter in order to derive a cause-effect relationship, which were deterministic cause-effect relationship relating the displacement with the damage. Starting from this and applying a probabilistic approach, we derive fragility and vulnerability curves till the estimation of risk. Now I will follow, I will give you also some other details about the methodology, then go into the results. First of all, we said that we had to, in the second phase, we had to define which was the damage severity ranking. The road was distinguished from the road pavement and the retaining structures, and we classified the damage first on the road pavement, going from D0 to D3, from negligible, let's say, to the severe damage, consisting, as you can see here on the photos, going from deformation, some cracks, and some dislocation of the road till the severe damage D3. Then, after the classification, a computation of the costs for repairing these different types of damage was computed, referring to a road, a typical road with a width of 7 meters. Then moving to the retaining structures in the area, mostly consisting of gravity walls, L-shaped walls, or bulkheads. Also in this case, as you can see here from the map, from the photos, a different distinction of the level of damage was carried out. You can see here this bulkhead, which was tilted due to the displacement occurring on the road due to the landslides. Also, in this case, the cost of repair was computed, but in this case, just referring to D3, which was considered the reconstruction costs, because in the area we identified that indeed the repair to the structures was not carried out until it reached the D3 level. Another key step before going to the result was the comparison. We said the validation of SAR data with ground-based data. In this case, we compared the displacement with derived from permanent scatters with GPS. On the left, here up, the first two graphs show the comparison of the velocity from SAR and GPS projected along the line of sight of the sensor. As you can see, both for Sentinel, the first two graphs, and for Cosmos Skymed, the second graph, we can see that the accuracy of the measurements from SAR data fall within this threshold, that is this gray strip, that is among 1.5 to 2 millimeters per year, which is typical in literature. So after validating our data set from SAR data, we derived, first of all, these velocity maps with the projection operation of the velocity of SAR along the loss, from the loss to the slope. So you can see here the vector maps derived from Sentinel and Cosmos Skymed with the vectors colored according to their magnitude of the velocity. Then, for each one of the landslides, the landslides were associated. As you can see here, they were colored according to the velocity derived from SAR data. Then, all the information and the first goal of the phase one was achieved. The landslide characterization was accomplished in this map, in which you can see that all the landslides are clusterized, are typified, let's say, according to their typology. For the one that has the same depth, you can see we go from shallow landslides to the deep landslides, that is the biggest one, according to the, of course, the environment, the involved geomaterials and their velocity. This was the first step of the analysis, the first results, the landslides characterization. Then the second phase was more focused on the damage assessment. First of all, multi-temporal damage field surveys were carried out. During the damage survey, this kind of fact sheet was filled in which you general information about the road, about the landslides were collected, about the location of the road, the typology of the landslides, and also the description of the road. In this case, it was a primary road, a starter road, and the description of the retaining structure, the description of the state of maintenance of both the pavement and the retaining structure. And here you can see some photo collection of the same point, in which you can see that we have images starting from 2004 until 2005. 2005 till 2021. In this case, some photos were taken from the archives of the National Research Council. Some other one, the one for instance here in which you see the label SS, they are from Google Street View. This allowed us to follow the evolution of the damage on the road and or the retaining structure over about 17 years. From this, we derived, for collecting the damage information for all the damage section of the road, we derived this map of the damage of the road section. And here, the second map, in which the road is distinguished with the different stretches with the level of damage of the retaining structures. By putting all together this information all together, we got these different multi-temporal damage maps, starting from 2008, 2011 until 2021, in which the road is colored according to the level of damage which was recorded on the different stretches of the road. This is again the map of the road. You can see here, this is the road track covered by permanent scatterers. Then at this stage, around each damaged section of the road, this is the road, the damaged section, the number of PS was computed following within a buffer of 10 meters. Within this buffer, the velocity were first of all projected along the slope, and then they were averaged. So each one, for each section, we derived an average velocity which was multiplied by the time to get the cumulative displacement over 3 years. In this case, you can see here in this histogram, you can see the track is a section from A to B along the road track, in which the cumulative settlements are represented. And as you can see here, we have the most active portion of the rock slide is this one, following within this first step, more closer to the Acre municipality. Then for each section at this stage, we had the level of damage and the intensity parameter, which was the cumulative displacement. These information were collected within this diagram, in which you can see that each star represents a section of the road which with its own damage recorded and the cumulative settlement that was derived from star data. As you can see here, we see that as the cumulative displacement increase, also the level of damage increase. Then from this diagram, it was derived on the right a frequency diagram, in which you can see that distinguishing in different ranges of the cumulative displacement, you can see that with the increase of the cumulative displacement, of course, we have the lowest level of damage decrease and appears the highest level of damage. Then, as it is well known in literature, from this map, it was possible to derive an empirical fragility curve by applying this formula, that is the log normal distribution function, in which you have the empirical fragility curves which relate the level of, for each cumulative displacement, they associate the probability of reaching or exceeding a given level of damage, in particular the 3 levels of damage that we considered, D1, D2, and D3. Then from fragility curves are started to be used in seismic engineering, and then more recently have been also mutated to landslide risk. From fragility curves, also vulnerability curve can be derived from by applying this formula, in which that is a kind of weighted damage, weighted on the probability of occurrence derived from the fragility curves. This curve relates, for if you enter this curve with a given displacement, you can get the expected level of damage. So, and in this case, the real data that are these circles were fitted with a tangent hyperbolic function. The vulnerability curves was used in this research also as a forecasting tool. How? Indeed, we noticed that we were informed with the more long-term study. We understood that in the area, the repair to the street, to the road were carried out at maximum every 3 years, so that with the assumption that the velocity of displacement was kept constant over 3 years, we multiplied the velocity by 3, and for each road section we were capable to compute the cumulative displacement in 3 years. So entering the curve for each section, we derived the expected level of damage that in 3 years should be expected to the road section. And by collecting all the information, we derived this map in which you can see the road track, which is colored according to the expected level of damage in by the end of 2024. As you can see, by the end of this year, most of the road is expected to get a severe level of damage if no countermeasures are taken. From this information, of course, it was also possible to make a comparison, because also on the cost for repair, so that is the third risk associated to landslides in this case. And it is interesting to note that if no countermeasures are taken in these 3 years, the expected damage loss, economic loss in 2021 was around 120,000 euros, whereas by the end of the 2024, the expected level of damage is more than 4 times. It's around 500,000 euros. Most of all because in these 3 years it was computed that most of the retaining structures, if no countermeasures are taken, will get to the highest level of damage, which usually requests for a repair in order to not have the road blocked, stopped for the circulation for a given period. So this was a way to use SAR data for within probabilistic tools that are the fragility and vulnerability curves, in order to reach risk estimation, also quantitative risk estimation over 3 years of forecast. So going to the conclusion, we can say that in our study, we developed a quantitative risk assessment for road interacting with the slow-moving landslides, and the novelty was here the combination of SAR data, remote sensing data, but also Google Street View imagery, in order to get on one side this cumulative displacement, on the other side information on the evolution of damage that indeed represents the interaction of the road with the landslide body. Another important step was considering the road as a whole, not only the pavement, because in the area the pavement is more easy to be repaired than the side retaining structures, which are more repaired just 5 times every 3 years. Then the reconstruction of the damage evolution, which was related to the cumulative displacement in over 3 years. Of course, these are the tools that can be more and more tested, but indeed they could provide, especially for expeditive analysis, because the aim was to identify which were the section of the road which in 3 years may reach a level of damage that is no more acceptable, and on which the prioritization of costs of money should be addressed. Thank you for your attention. Here you see my details. Of course, there is also my by mail, and I will be happy to answer to your question or any contact with you and with all the audience. Thank you.
Thank you so much, Dr. Dario Peduto. It was
Yes.
an exceptional presentation. I am very glad you presented today.
Yeah.
And I invite all those who can contact or ask questions to Dr. Dario Peduto. Feel free to write in the live chat or send in an email as he just invited. Thank you so much, Dario.
Thank you. Thank you very much. Thank you to all. And I hope you enjoy the continuation of the conference. Bye. Thank you.
Thank you. So we are back, and I am honored. I am very happy to introduce Dr. Michael Long. Thank you so much, Professor, for accepting our invitation to present at the Landslide Scientific Assessment Conference. It is all your time, but please, before you start with your presentation, as I have requested other speakers, can you please introduce yourself, tell us a little bit about your research, and then you can start. Thank you so much.
Of course, thank you, Roberto, and thanks. It's obviously lovely to see you yourself, and it's really nice to be here. So, as I was saying to you, my presentation is perhaps not as technical as some of the previous ones, but I hope just to introduce everybody to some Irish soils and to some work that's ongoing here in Dublin. So my name is Mike Long, and I'm a geotechnical engineer. Work here in University College Dublin in Ireland, and my research topic has been on the characterization of natural soils. So looking at the properties of natural soils, using in situ tests and lab tests, and then applying that work to real life problems. This presentation here is together with our conference chair, Roberto. Roberto was a research scientist here in UCD for 1.5 years and did some really nice work. So this work I'm presenting is also his. And we worked together with a consulting company called Arup. And the project was on the long term, or the project is, it's an ongoing project. The project is on the long-term geotechnical performance of earthwork slopes in Irish glacial tills. Okay, I hope I can make this slide go to the next one. Okay, thank you. Our client in this project is the Irish Transport Infrastructure Ireland, who are the Irish body in charge of all of the main roads and railways in Ireland. And TII, together with many other similar organizations throughout the world, face significant challenges with respect to the long-term maintenance of their highway networks. And they're obviously concerned with long-term weather effects and with climate change. So what they asked us to do was to investigate and to monitor the geotechnical behavior of one cut and one embankment on the Irish motorway network. In this presentation here, I'm going to focus on cut slopes. Embankments are perhaps a job for another day. Now, this is a topic that has been researched in other places, and I'm sure many of you are familiar with that. Perhaps the most notably in the UK, there has been two significant research projects called iSmart and Achilles, which have similar objectives to this study. But those studies both were dealing with the UK soils, which are very different from the Irish soils that we're dealing with here. So this slide is from the Achilles project, from one of the publications on the UK Achilles project. And what it shows on the y-axis is the performance of a geotechnical asset, and on the x-axis it shows the age of the geotechnical asset. And if you follow the graph from left to right, you will see that we're following the blue line here. You will see that initially there's a period where the asset's very new and it's bedding in, and its performance is improving with time, and then it reaches a plateau, and perhaps for a long time, the performance of the asset is very reliable. But then some time will come eventually when the performance of the asset begins to deteriorate, and eventually it will become unreliable. What I'm focusing on here, and what our research focused on was the period of deterioration. So what causes the deterioration in the particular assets that I'm talking about here? So this is, excuse me, this is a geological image of Ireland. You can see, if you focus first of all on the image on the left-hand side, this is Ireland here. Dublin is located here on the east coast. There's a lot of detail on the slide, but if you focus on maybe on the brown colors on the left-hand side, and these are glacial lodgement tills. So these are materials which were laid down underneath the glaciers during the retreat of the glaciers in the last ice age some 10,000 years ago. And you can see these brown colors dominate the country. So these glacial lodgement hills are of significant importance. On the right-hand image, you can see two colors. The green colors refer to these glacial tills, which are derived from limestones, and the the orange colors derive from glacial tills, which are derived from sandstones and shales. And you can see that and the motoring network, or the national road network, is shown by the red lines. And you can see that these glacial tills are of significant importance with respect to the road network. So the research site that we chose, based on a lot of very nice work by Roberto, is located where you can see the black dot. It's located near a town called Castleblaney in the north of Ireland, and it's on a road called the N2. So this is the slope that we're interested in. This is a really classical Irish slope. You can see that the road, which is in this case is a 2+1 motorway, has been cut into the hillside here. And in Ireland, the standard practice is to use a cutting of 1-on-2, so 1 vertical to 2 horizontal. Perhaps a little bit conservative, but that's what's used. And this slope is about 8 meters high. And you can see one of the nice things about this slope is that there's a nice access road at the top of the slope, which allows us access to the top of the slope. So I think this slope was a good choice. It's characteristic of the soils in Ireland, and it's characteristic of the construction techniques used in Ireland and in other places. So just to get into some details of the soils here, and perhaps maybe to show why they're a little bit different from soils you find in other places. So this is a particle size distribution curve, which shows the percentage passing sieve on the y-axis and the particle sizes on the x-axis. The blue lines are from our site. And you can see that the lines form an approximate straight line relationship. And this is a classical, what's called in geological terms, is called a diamicton, a glacial till, where you get this very linear graph of percentage passing versus particle size. So there's a large range of particles involved, and this is why these materials can compact very well. I'm going to compare these soils to a well-known soil called Dublin boulder clay, which is the soils which are underneath my feet at the moment here in Dublin, and these soils have been very well characterized. You can see our soils, the blue curves, are a little bit coarser than the Dublin boulder clay, but they're broadly very similar. We like to use basic index properties to characterize our soils. And here you can see the water content on the far left-hand side from the N2 site. The water content is some 10%, so it's relatively low water content. Again, the plasticity index is also relatively low, about 8% on average. And on the far right is the liquidity index. Liquidity index is equal to the water content minus the plastic limit divided by the plasticity index, is always negative, so maybe typically minus 0.8. And this tells us that this is a very competent glacial material, and it's likely to be very heavily over-consolidated. So these materials are excellent, provided you leave them alone, provided you protect them, and provided you don't expose them to weather changes. So this is a picture from a site very close to where I live in Dublin, and here the developer dug a very deep, relatively deep, 6 meter deep, steep cutting into the Dublin boulder clay. Of course, what he was trying to do here was maximize the number of apartments he could fit into this site. But you can see here that the material is standing at approximately 90 degrees, and it stood there at the steep angle for a relatively long time before a retaining wall was built in front of it. It was a brave piece of operation because he was cutting right next to his neighbours there, just behind the cutting. So these materials are well known to be able to stand unsupported for significant long periods. And of course, what's allowing this to happen is that when the excavation happens, some suctions are induced into this material. And because it's so low permeability, these suctions can be sustained for a long period, allowing these materials to stand up. However, this is not a stable situation, and weather-induced and climate-induced effects are going to change this rapidly. So the fact that these soils can stand unsupported for significant periods of time was used by engineers in a constructive way during the construction of a large tunnel project here in Dublin called the Dublin Port Tunnel. This tunnel is just north of the city on the road to the airport. It's on the M1 motorway, which is the road between Dublin and Belfast, and passes by the airport. The contractors were forced to divert the traffic on the M1 to both sides of this cutting during the construction process. And in order to facilitate this, they cut a very deep excavation, probably 12 meters high or so, at 70 degrees into these glacial till materials. And this was a significant project, was approximately 1.2 kilometers long. It's called cut and cover construction. So ultimately the tunnel was built and the whole area was covered. Some soil nailing was used to reinforce the slope, but broadly speaking, the ability of the soils to stand unsupported was used in the technique. Now we had to impress to the client this technique would work. So here is a picture of a trial trench that we dug prior to the main works. This mimics the main works in that it's about 12 meters deep. The material is cut at an angle of 70 degrees, and you can see that there's some protection measures applied to the exposed material here. Plastic sheathing on one side, some shotcrete, some sprayed concrete on the other, and there's also a few trials of some soil nails done. So using this trial, we were able to demonstrate that this technique would actually work in practice. And again, just on suctions, and this is something that we've done really just for our own sake, just in order to try to get a feel for what's the variation of these suctions in the Irish glacial tills with time. Now, this is not a cutting, this is an embankment. It's an embankment in a hydroelectric scheme on the River Erne in the north of Ireland. And again, it's a relatively long embankment, 6 or 8 meters high. And it's made of glacial till material, very similar to the ones I've just been talking about. And we put some tensiometers into the embankment here. And these are just agricultural style tensiometers, can measure suctions up to maybe minus 100 kilopascals. And we really wanted to see what was happening over the year, so everybody knew, everybody could understand what was going on with these materials. And I've just taken a snapshot here of data for 6 months. And what I want you to focus on here is the blue dots. So these are the tensiometer suction readings, and suction is shown on the y-axis and time is on the x-axis. And you can see that the values vary between small positive values, plus or minus 2 maybe, to minus 10 or so kilopascals. And if I'd shown all the data, and I haven't shown it here because I didn't want to confuse everybody, you can see that over a period of years, the suctions will cycle between plus 2 maybe and minus 10 in 6 monthly intervals. So I suppose the question is, what is the long-term effects of this cycling of the suctions going to be, and how is it going to affect the geotechnical assets? And that's really what we want to find out in this project. So what you will see is something like this. This is a temporary slope. Again, in a construction project, the slope is, in this case, perhaps 5-6 meters high, was cut very steeply into the glacial till materials, was left unprotected for a period of time. And again, you can see that there's a gradual deterioration in the slope. And this is due to weather-induced changes. So the suctions that were developed have been eliminated by the weather here. And what you see then is the slope deteriorates and the material slides off in relatively small wedges. Now here the consequences weren't significant because it was just an access road to a construction site, but it does indicate that this is what could happen to these geotechnical assets, in the long term if they're not carefully looked after. This is a similar cutting. This is actually in Dublin Airport, if any of you have been there. This was an excavation for an underground baggage handling facility. The contractor cut a very steep slope in the Dublin boulder clay here, trafficked up and down adjacent to it with trucks, as you can see. And the suctions, again, diminished over time. And due to the lack of suction and due to the loading that was applied, you got, again, shallow failures. We would call them flakes in English. So it's like you get these shallow slides sloughing off the surface of the embankments here. So this is what happens. And this, of course, is what we want to guard against with the motorway network. And just going back to my trial trench. So this was the trial trench for the Dublin Port Tunnel. And there was one section of the trial trench where the contractor encountered a small granular lens. And of course, the effect of the granular lens was to allow rapid release of the suctions which had been induced. And that release of suctions allowed the effective stresses to reduce, and therefore the strength reduced, and you got a failure like this. And again, what you see is you don't see a very deep failure like you might see in a soft clay material, but you see a relatively shallow wedge-like portion of the soil sliding off the face of the embankment, of the cutting in this case. So with all these things in mind, we've gone on to make a plan for the work that we're going to do on our project site. So this work is ongoing, and maybe this time next year I can come back and maybe give you some of the results of what's happening on the site. So as I explained, we have access to the site due to a nice access road at the top here, and we intend to install 2 boreholes, and we're going to take cores of the material. We're going to use a GeoBore S coring technique. This is a triple tube coring technique, which is very suitable for these very hard glacial tills, which have a high stone content. So we're going to get some GeoBore S cores, which of course we will test in the lab. In one of these 2 boreholes, we're going to install an inclinometer to look at the lateral movement of the slope in the long term. And then the other, we're going to install some piezometers. And these piezometers will have a suction measuring device, because I think you can see that suctions are key here, and we're keen to understand what's happening to them in the long term. On the surface of the cutting, we're going to install some shallow suction measuring instruments, and we're also going to install some instruments with which we can monitor the volumetric water content changes in the slope. We're going to try to use satellite monitoring, as been the case in several of the presentations at this conference so far. And we're going to mount some surface mounted reflective targets to help the satellite monitoring. And of course, we're going to have a weather station as well. So the next steps in this project are to drill these boreholes and do the samples and install the instruments, as I explained. And then we plan to monitor the slope for as long a period as is possible. But in parallel with that monitoring, we intend to develop a numerical model, and Roberto has done a lot of work on this and has published actually some papers on the suggested numerical models which might be appropriate for this work. Then the idea is to try to match the model with the monitoring we get from the instruments on the slope. And of course, the ultimate objective is to attempt to apply these lessons widely to the Irish motorway network. And our hope is that our client, Transport Infrastructure Ireland, will be able to make some better plans about their asset management and on their maintenance scheduling into the future. So that's all I have to say. Thank you very much for listening. I'm obviously happy to take questions. And Roberto, you probably know more about this project than I do, so especially the modeling side. So I'm not sure if you wanted to add anything to that.
Oh, I am very glad to hear your excellent presentation. Thank you so much. As we have done with other presentations, feel free to write questions or comments in the live chat. But thank you for all.
Roberto, I'm obviously very happy. If anybody has any questions or about these materials or about the modeling, I'm very happy to take them. And obviously we have the 2 papers that you've published. We'd be very happy to point people in the direction of those papers if they're interested in learning more about these materials and what we've been doing.
Sure, for sure. And also some ideas from my side you will find in the same channel, the YouTube channel of LandScient. You will see actually about one of the papers that Professor Michael Long has referred. So I don't find right now questions, so I want to thank you for
You're welcome, Roberto.
your excellent work. I can also say that from your side as an excellent person and my boss and supervisor. I am very, very glad that I learned so much from you, and now to have the opportunity of hearing you in the moment that we are carrying out this event so important for land science. So
Thank you,
thank you so
Roberto.
much.
And absolutely, it was a pleasure to have you here in Dublin too, and I enjoyed working with you as well.
Thanks. This is day 3 of the Landslide Scientific Assessment Conference. I am just waiting so that my face looks a little centered, but I want to say goodbye. I want to thank all the speakers, authors that participated in this event, the Landslide Scientific Assessment Conference, Slope Dynamics. We learned a lot. We will find in the same channel, we are going to find the individual presentations. It was a wonderful experience. I hope that you stay connected with us and we continue learning, teaching others, sharing what we are doing in our research, specifically as we have emphasized so much to save lives. This is the purpose of land science, probably, and are certainly most of the researchers that are studying landslides, top researchers worldwide, that they presented in this event, they are also interested in the same goal, the same aim of saving lives. So I am going to say goodbye to all of you, and thank you for being part of this event. God bless you so much.